right, sound check, sound check. I'm hearing audio. Let's see if visuals are working. Do I see movement on the screen? Yep, that looks good. All right, time to put away the headphones. And get started. This might be the last lesson before the sort of, I don't even know what to call it, study guide mini review thing that I have planned for after this. I'm hoping that I can just get it all done today. It might have to be split into 2 parts, but I would really prefer to just get it all done at once because I just want to be done with this. So yeah, if this has to go for like 5, maybe even 6 hours, then I might actually dare to do that. I might actually end up doing that. So last time we covered, for the most part, we just covered like very, very basic calculus. I didn't go super into detail. I didn't really prove every single relationship that we used, and we didn't even go over special rules for differentiation and integration, like the product rule for differentiation or the integration by parts technique for integration, because, well, those aren't going to be tested on your AP exam. You can learn those things in the AP Calculus course if you really want to know more about that stuff. And actually, come to think of it, I still haven't timestamped that live stream, so I'm going to need to get on that at some point during this week, put those timestamps in. But anyway, we covered very basic calculus, not a lot of examples. I'm sure it might have not been super clear to some people at some points, but today part of the goal is to actually try and clarify some of that stuff through actual examples applied to physics. So we're gonna basically introduce calculus when and if it applies to each of the chapters that we did in our physics course, and each chapter has at least something. Let me think. What else did I want to say here? So yeah, the plan is to just do some problems that involve the use of calculus, at least a few for each chapter, but also introduce any new equations. So it's not all going to be problems. We're also going to introduce some new equations using calculus, some integrals and some derivatives that you may have not thought about before as being opportunities to use calculus. And I think that will be it. So without further ado, let's begin. I have some notes, but the level of structuring isn't exactly what I would have preferred. So let me see what I have on my notes. First up, for the kinematics chapter, and by kinematics I'm also including projectile motion in that. So in kinematics, really the main opportunity to use calculus will be whenever you have a variable acceleration. And when you have a variable acceleration, that also means you have a variable force. So there might be some overlap with the force chapter here. The main variable force that you will deal with will be air resistance. So calculus might be needed for air resistance. Calculus may be needed for a variable acceleration in general. Calculus is needed in kinematics when acceleration is variable. When acceleration is variable. Hesitated about the spelling of acceleration for a second there. And again, the main situation you'll encounter with a variable acceleration, it's not the only one, but the main situation you'll encounter will be situations involving air resistance. So air resistance is common. And air resistance tends to come in two common forms. So air resistance is a force, sometimes called the drag force. You'll often encounter it in this form, negative BV, where the negative sign just means that the force is opposite to the direction of the object's velocity. And the other form you might encounter is, instead of this linear air resistance, you might encounter a quadratic air resistance. And I guess squaring a vector, we won't get into how squaring a vector works here. That's something for future courses that you can take. But yeah, you might encounter drag force having a formula of either negative BV or negative BV squared. And of course, in the real world, it's usually some combination of the two. Usually one of the terms, either the linear or the quadratic term, predominates, so they simplify it down to just being linear or just being quadratic. But in real life, you will have air resistance formulas that have like one constant times the velocity to the first power, and then another constant times velocity squared, all in one equation. Like you might have a more general drag force equation that looks something like this. And maybe there's even like a cubic term. Maybe there's even a plus in here somewhere. It's been a while since I've actually done one of the higher physics courses that dig into air resistance, so I'm not entirely sure. But something like this, if you do some experiments and you try to calculate, how the speed of something changes, you might end up with a formula like this. If you plot a bunch of data points, you might find your best fit polynomial is something of this form. In any case, we're not going to worry about this. You're typically going to be given this form, and on rare occasions you might get the BV squared form of air resistance. Those are the two that you will typically have. More often this, because this is easier to do calculus with. So if you get air resistance in a question, this will be what you typically get. If you get this, they will probably tell you to set up the calculus without actually doing it, because doing the calculus in this form requires an integration technique that you would not have learned unless you did calculus BC. So let's go ahead and look at some kinematics questions with variable acceleration. We'll probably introduce air resistance somewhere later down the line, but let's go ahead and look for some questions here that actually use variable acceleration or just calculus in general. Let me see what I have in my notes. So it looks like we've got this first one here says an object is moving with velocity given by, okay, so this is more practice with unit vector notation. Something else I should have mentioned in the introduction today, but I forgot. The other thing that we're going to be doing aside from calculus is practicing a little bit with unit vector notation, which I also introduced last time, just in case they ask a few questions here and there using that notation, but also to make sure that you're not going in completely blind if you end up taking a college physics course where your professors expect you to know this stuff. So it says an object is moving with velocity given by v of t equals vx of t I hat plus vy of t j hat plus vz of t k hat, where vz of t equals 0, where vz of t equals 0. So I guess it's just a two-dimensional velocity then. We don't have any velocity in the z direction, which is fine. It says from this, one can conclude that the acceleration a of t is, it's a multiple choice question, so a of t is, answer choices are, A will have no components that are 0, will have no components that are, well, it says identically 0, no components that are identically 0, and by identically 0 they just mean since they're v of t functions, there might be a time when they're 0, and maybe it's just that one specific time that they're 0, but they're not always 0. So what it's saying, what it means by will have no components that are identically 0. Identically 0 means that it's 0 for all times t, which might be one of our answers. Second answer choice is may have some components that are identically 0. May have, maybe I shouldn't have actually picked this problem. Writing this is taking too long. May have some components, and then components that are identically 0. C will have only a z component, will have only a z component. That is identically 0. I'm just going to say 0. Or D will have an identically 0 z component and maybe will have a z component of 0 and maybe an identically 0 component in the x or y direction, and maybe a component of 0 in x or y. I don't even know why I added this problem to the list. I think I just saw unit vector notation and went, cool, go with it. Probably should have put more thought into it than that. But anyway, So acceleration is going to be the derivative of velocity. So if we take the derivative of this, knowing that vz of t is equal to 0, all you have to do is differentiate each term one by one. So acceleration as a function of time is going to be the derivative of vx of t. Well, that's just going to be ax of t I hat, plus, for the next term, derivative of vy of t, we'll just call that ay of t. We don't know anything about what vx and vy are, so this is the best we can say for now. Plus, we know that vz of t is 0, and the derivative of 0, as you can imagine, is still 0. So we can say plus 0k hat, or better yet, we can just not write anything at all over here. So we've got an unknown function for our x component and an unknown function for our y component. So the only thing we know for sure is that the z component of the acceleration is 0. We don't know anything else, so all we can really say, we definitely can't say that a is right because we do have one component that's 0. May have some components that are identically 0. Well, it's not may have, there's definitely a component that's identically 0, so it's not b. We definitely have at least one component, so same reason really that a is wrong, b is wrong. We'll have only a z component that's 0. Not necessarily. The x and y components could be 0. The simple fact of the matter is we don't know. So yeah, D is the right answer there. Okay, and then the second part of the question says that the position r of t, the second question says r of t will have no components that are identically 0, may have some components that are identically 0, will have only a z component that's identically 0, or will have an identically 0 z component and maybe an identically 0 component in the x or y direction. So actually the same 4 answer choices as before. What about r of t? What about r of t? So r of t, position, would be the antiderivative, the integral of velocity. So r of t is going to be integral of v of t with respect to time. So I would integrate each of these terms, and if I do that, then I get r of t equals, if I integrate vx of t, then I get rx of t, or I guess we'll just call it x of t, really is a better way to say it. X of t times I hat plus integral of vy of t would just be y of t times j hat. And these x of t and y of t terms, by the way, they include the plus c of the integration. So even though I'm taking an indefinite integral here, I don't have to write x of t plus c, because that just means it's a different function of t that has the plus c in it. I guess one way to think about it would be to say, for example, let's say, for example, that I have x1 of t. Maybe if I knew something about vx of t and I did the indefinite integral, maybe I got something like, I don't know, 3t to the 5th for my x1 of t. And then I did integral of vx of t dt equals this 3t to the 5th plus c. Well, then I could just put that plus c, whatever it is, into a new function x2 of t. This probably isn't making that much sense. And just have that plus c already included in it. So since I don't know what my x of t is, I can just basically whatever my x of t is, whatever this is, it doesn't even matter. This was just something I threw in for example. Whatever this is, if I just throw in the plus c with it, since I don't know what this is anyway, adding something I don't know to some constant that I don't know still results in some unknown x of t function anyway. So that's why I don't need to write the plus c in here. And then, where were we? So before that detour, we did x of t I hat plus y of t j hat. And then for the third term, we know vz of t is 0. And what's the integral of 0? Well, the integral of 0 is a constant. Right? 0 is the derivative of a constant. So this is going to be plus some constant, which might be 0, but it might not be. Plus some constant. I will call it z0. K hat. So it's definitely not a z of t, but some constant that may or may not be 0. Okay, so this changes things a little bit from what we got for acceleration. So let's see, we'll have no components that are identically 0. Not necessarily, because this z0 constant could be 0, so it's not a. May have some components that are identically 0. Yes, we don't know for sure, but it may have at least one component that's identically 0 if z0 over here is 0, or actually if any of these three are 0. So B so far looks like it might be right for this question. We'll have only a z component that's 0, not necessarily true. We'll have a z component of 0 and maybe a component of 0 in x or y. Again, the z component is not guaranteed to be 0, so actually B would be the answer for the position version of the question. Okay, that was probably not the best question to start off with, but at least we have something with unit vector notation. At least we've got that covered. Let me see, this next one. An object is moving in the xy plane with the position as a function of time given by r equals x of t I hat plus y of t j hat. Point O is at r equals 0. The object is definitely moving towards the origin when, and then you've got A, B, C, and D. Okay, let's look at this one. It might actually require, does it require product rule? Because if it does, then we have to skip it. Actually, no, I think it doesn't. Okay, so we are given a position function, r of t, equals x of t I hat plus y of t j hat. We don't know what x of t or y of t are. We just know that it has some sort of two-dimensional position function, and also we know that point O, the origin, is at r equals 0. Point O is at r equals 0. That is 0 x component, 0 y component, and yes, if you're thinking in 3 dimensions, 0 z component as well. So it says the object is definitely moving toward O when, which of the following? A, Vx greater than 0, and Vy greater than 0. B, Vx less than 0, while Vy is less than 0. C, when x times vx plus y times vy is less than 0, or D, or choice D, when x times vx plus y times vy is greater than 0. So those are the answer choices. Let's see, how do we know if something is moving towards the origin in terms of its velocity and maybe in terms of its position? Well, let's draw a coordinate system and see what that looks like. So let's say, for example, so here's your origin O, and let's say at some point in time you are over here. Or maybe at some other point in time you're over here, or at some point in time you're over here, or somewhere over here. Let's just cover one random point in each quadrant. How do I know if I'm moving towards the origin? Well, it depends on where I am. First off, it definitely depends on where I am, and it also depends on which way I'm moving. If I'm over here and I'm moving left, that's towards the origin. If I'm moving down, that's also towards the origin. But if I'm moving right or up, that's not necessarily towards the origin. But also, what if I'm moving left but also up? By moving left, I'm moving closer to the origin, but by moving up, I'm moving further away. So which of those effects predominates? The one thing that we can say for sure is that you are getting closer to the origin if the magnitude of r. You are getting closer to the origin if the magnitude of r, is decreasing. R is going to be measured from here to here after all. If the starting point is the origin, then the magnitude of r would have to be equal to the distance from the origin. So let's go ahead and calculate the magnitude of r. Let's get an expression for the magnitude of r. The magnitude of r, or r of t if you prefer, is equal to, well, the magnitude of any vector is just the square root of the sum of the squares of its components. So it's going to be equal to the square root of x of t squared plus y of t squared. Oh, and I think I see that this requires a calculus technique that you guys haven't learned and aren't required to learn for AP Physics. Well, some of you may have learned it if you're taking calculus. Okay, I can already see the problem here. So I'm going to square both sides of this. Magnitude squared equals x of t squared plus y of t squared. Okay, so yeah, this is going to require, whoops, forgot the square there. This is going to require something called implicit differentiation, which I did not teach you guys last time, and you're not expected to know for the AP exam, but you might be able to accept it if you remember what I covered regarding chain rule. So what I want to do is take the derivative of r of t, or rather the derivative of r of t squared. It shouldn't matter either way. What I'm trying to figure out is when the magnitude of r is decreasing. And to figure out when something is increasing or decreasing, we can look at its derivative. If the derivative is positive, then it's increasing. If the derivative is negative, then it's decreasing. So we are looking for when the derivative with respect to time of r of t, or the magnitude of r of t rather, is negative, is less than 0. And if the magnitude of r is decreasing, then the magnitude of r squared is also decreasing. So we can still use this as well. We can still take the derivative of r squared instead and see where that is less than 0, and that would still work. So if I take the derivative with respect to time of this whole expression, if I take the derivative of this whole expression with respect to time, then what do I get? Well, this is going to be a chain rule problem, because what I really have is a square function, and then inside of that square function I have this r of t function. That's what we talked about last time with chain rule. When I have a function inside of a function, like sine of x squared, for example, if I were taking the derivative of this with respect to x, I've got a function x squared inside of another function sine of x. And what we would do is we would take the derivative of the outer function, rewrite the inner function, and then multiply that by the derivative of the inner function. The derivative of x squared by the power rule would be 2x, and of course, to make it look nice, I would write it with the 2x in front, like so. Another example would be, let's actually just reverse this. Let's do the derivative with respect to x of, I'll have the square function outside of the trig function. So what's the derivative of the square of sine of x? Well, that is going to be, the derivative of something squared is 2 times that something to the first power, and then times the derivative of the inside times the derivative of cosine of x. Right? That's chain rule. We covered that last time, although we didn't really do that many examples of it. And then, so if we apply chain rule over here, the derivative of r of t squared, well, it's a square function on the outside, so it'll be 2 times whatever the magnitude of r of t is, times the derivative of the inside, times the derivative of the inside, so times d magnitude of r of t dt. Okay, equals derivative of x of t squared. It's going to be the same thing, 2 and then x of t to the first power times the derivative of x of t with respect to time. We know what that is. The derivative of x of t with respect to time, that's the velocity in the x direction. You could have kept it written as dx of t dt, kind of the same way I did over here, but you don't need to do that because we already have a name for the derivative of x with respect to time. It's velocity in x. And then plus, do the same thing with y of t squared. If I take the derivative of this, I get 2 y of t times derivative of y of t with respect to time, which is equivalent to Vy. Okay, we can cancel out all these 2's. And then what I have left is I want this derivative, right? I want the derivative of the magnitude of r of t with respect to time. I want the derivative of this to be less than 0. So I need this to be less than 0. The magnitude of r of t is going to be positive or 0. So that's not, so we can just divide both sides of the inequality by magnitude of r of t, and that won't change anything. Let me do it over here. So d magnitude of r of t dt, I want that to be less than 0, and I've divided by magnitude of r of t. In all cases except when r of t is already 0, zero divided by this is just going to still be 0. So then actually, let me think this through. I didn't explain this really well. Let me try and explain my reasoning here. So we are looking for when this is less than 0, and this is less than 0 whenever this times magnitude of r of t is less than 0. So actually what I should have done is start with this, multiply both sides by magnitude of r of t. Yeah, there we go. What we're looking for then is when this expression over here is less than 0. But this expression over here is equivalent to x vx plus y vy. So we are looking for when x vx plus y vy is less than 0, and that means it would be choice C. But now let's actually try and reason through this and see if that actually makes sense. So when x times vx plus y times vy is less than 0, that means either x times bx needs to be negative, or y times vy needs to be negative, or both. And when they're not both negative, whichever one is negative needs to be more negative than the other one is. Hold on. No, that didn't come out right. If only one of them is negative and the other one is positive, the one that's negative has to have a greater absolute value so that the total is negative. That's what I meant to say. So let's see if that makes sense. When x is positive, I would want vx to be negative. That's kind of what I was saying earlier. If you're either here or here, somewhere to the right of the origin, then moving to the left would decrease your distance from the origin. What about for y vy? Same idea. If your y is positive, you would want vy to be in the negative direction. If you are down in the negative, if y is negative, then you would want vy to take you up to get you closer to the origin. So each of these terms individually needing to be negative makes sense, but also it addresses the problem I mentioned earlier. What if, for example, you are moving closer in terms of x, but you're moving further away in terms of y, or vice versa? Well, then you just add both effects, is basically what this is telling us. You add both of those effects, and whichever effect is greater, if x vx is more negative, then y vy is positive. If I was moving to the left and up, if my x vx, the leftward part of my movement, is greater than y vy, the upward part, then I would be moving left faster than I'm moving up, so overall I would actually be getting closer in that situation. So yeah, this makes sense. this result does make intuitive sense when you sit down and think about it. Alright, that takes care of that one. What else do I have on my list here? Let me see what this one says. An object starts from rest at x equals 0 when time is 0. The object moves in the x direction with positive velocity after time 0. The instantaneous velocity and average velocity are related by what? So it moves in the x direction with positive velocity after time is 0. Okay, yeah, there is no real relationship. I don't know why it even asked us this question. But it's a multiple choice question, so we might as well take a quick look at it. This one's pretty easy. It's really just practicing with the meaning of the derivative, if nothing else. Otherwise, I would skip it. So it says the object starts from rest at x equals 0 when time is 0. So x of 0 equals 0. The object moves in the x direction with positive velocity after time 0. So we know Vx of t, whatever it is, it's greater than 0, it's positive. The instantaneous velocity and average velocity are related by which of the following? So the answer choices are A, dx dt is less than x over t, B, dx dt is equal to x over t, C, dx dt is greater than x over t, or D can be any of the above. And come to think of it, I mixed my capitals and my lower cases. What did I even do? Capital B there, and we'll make that a capital D. And I'll pretend that was always a capital C. And yeah, choice D says dx dt can be larger, smaller, or equal. So no relation, no particular relation can be determined. Those are your answer choices. All it said was that the object moves in the x direction with positive velocity. They never said if that positive velocity is constant, increasing, decreasing, anything like that. We don't know. So when it's asking about the instantaneous velocity versus the average velocity, well, the dx dt, that is the instantaneous velocity. X over t, that's the average velocity, right? It's just delta x over delta t, where delta x is x minus x0, x0 being 0, of course, and delta t being t minus 0 as well. So yeah, it just simplifies to x over t. So it's just instantaneous versus average for each of these three answer choices. Do we know for sure that the instantaneous velocity is less than, equal to, or greater than the average? No, we do not. It's equal to the average only if the velocity is constant. In all other situations, it would have to be less than it sometimes and greater than it at other times. Because if I were to look at a graph of, I guess we'll do position versus time. If I were to look at a graph of position versus time, and I were to look at it between 2 points, and let's say this thing is always moving upward, so I guess, so I guess that's not a good graph. Let me try again. So something that's always moving upward on a position versus time graph, maybe something like this. Okay, that's good. So if I draw a bunch of tangent lines, you'll notice that they always slope upward no matter which point I try to draw a tangent line on. So the instantaneous velocities are always positive. But the average velocity will just be if I start at time 0 and go to whatever time this is, the average velocity, the slope of that orange line, well, we see sometimes that slope is actually greater than some of these tangent lines, right? It's greater than that first one, and it's definitely greater than that last one, but it can also be less than the slope of some of the other tangent lines. Like here's an instantaneous velocity, this one over here clearly climbs higher, faster than the average velocity line does. So yeah, there's no particular relationship here. Next one on my list was this one. It says an object is moving in the x direction with velocity vx of t, and derivative of vx with respect to time is a non-zero constant. With vx equals 0 and t equals 0, then for t greater than 0, the quantity of vx times d vx dt is negative, 0, positive, or not determined from the information given. Okay, let's look at this. I'm starting to have regrets about some of the questions that I picked over here. So it says an object is moving in the x direction with velocity vx of t, so just moving on some horizontal line. It's moving with velocity vx of t. Velocity equals vx of t. And it's also telling me that d vx of t with respect to time vx of t with respect to time is a non-zero constant, equals some constant that is not 0. Does not equal 0. With vx equals 0 when t equals 0, so when vx of 0 equals 0, then for t greater than 0, the quantity vx times dvx dt is a negative b positive, or b 0, c positive, or d can't be determined. Can't be determined. Well, this tells me I have a constant acceleration, and if I have a constant acceleration and I start from rest, then my acceleration is going to give me a velocity that is in the same direction as that acceleration, and that direction isn't going to change. So after time 0, after that first moment, the direction of the velocity and the direction of acceleration are going to be the same. So either the acceleration is negative and the velocity will be negative immediately after you start the timer, in which case you have a negative velocity times a negative acceleration, or the acceleration is positive, in which case you gain a positive velocity, multiplying that by positive acceleration. Either way, negative times negative or positive times positive, the velocity times the acceleration should be positive in that case. So yeah, these have been, for the most part, just exercises in understanding the meaning of the derivative. Okay, let's see if we can find something that actually requires us to get some numbers. What did I list here? We'll do that later. I'll go back to that one later. Same thing for that one. Here, finally, we've got one that actually has some numbers we can work with. So it says the position of a particle. This next one says the position of a particle moving in an xy plane is given by r of t equals 2t cubed minus 5t I hat, so 2t cubed minus 5t I hat, so that's in the x direction, plus 6 minus 7t to the 4 j hat, 6 minus 7t to the 4 j hat. Calculate r, v, and a when t equals 2. Calculate r of 2, v of 2, and a of 2. Alright, so I'm seeing a t cubed here and a t to the 4th here. If the position function didn't go higher than t squared, then that would be a constant acceleration problem, and we could just use the equations of constant acceleration to solve this. But clearly, that is not the case here, so this is how we know you need calculus here. If it involves anything other than a combination of t squared and t terms and maybe constants, if it has like square roots, or in this case cubic and 4th degree powers of time, if it involves anything like that that you're not used to seeing, then it's probably a calculus problem. So r of 2 is easy, just plug in 2 for t and you're done. We can skip that part. V of 2 and a of 2 are also easy enough once you actually do the calculus. So velocity is the derivative of position. If you take the rate of change of position with respect to time, that is the instantaneous velocity. So just get v of t is equal to the derivative of r of t equals, let's see, if we're differentiating with respect to time, if we differentiate term by term for the x component, we've got derivative of 2t cubed, just use the power rule, multiply by 3 and decrease it by 1, so 2 times 3 is 6t, and then 3 minus 1 is 2, so that's t squared, minus 5t, that's 5 times t to the 1, multiply by 1, it's still 5, and then t to the 1 minus 1, that's t to the 0, which is 1, so just 6t squared minus 5. In general, the derivative of a linear term is just whatever the coefficient is. Once you've practiced this enough times, you should be able to do it just immediately without having to put much thought into it. But until you get there, just use the power rule on such terms and you'll be fine. Plus, in the y direction, we've got the derivative of 6. Well, the derivative of a constant is 0. And then plus the derivative of negative 7t to the fourth. That's going to be negative 7 times 4. That's negative 28. And then it becomes t cubed. Decrease the power by 1. And then that's going to be in the j hat direction. So yeah, it looks like we have positive velocity. Well, I guess it depends on t, but once t gets high enough, positive velocity in the x direction and negative velocity in the y direction, it seems, assuming t is greater than 0, or in fact greater than whatever t is necessary to beat this initial negative 5. But yeah, that's v of t, and now that you have that, all you have to plug in is 2 for t, and you would get v of 2. You know how to do that, so I'm not going to bother with that. The goal here is to really just master the calculus. Now, to get a of t, that's the second derivative. That's the second derivative of position, which is also just the first time derivative of velocity. And we already got the velocity as a function of time, so just take the derivative of this. Derivative of 6t squared minus 5 is going to be 12t to the first power minus nothing, because the derivative of a constant is 0, and then times I hat. And then we've got minus 28 times 3. Oh boy. Minus 90, and then add 6 back, so minus 84. So negative 84 t squared j hat. And to get a of 2, just plug 2 in for t over here, and you've got your x component, your y component, you're good to go. If it asked for the magnitude, you would then just square whatever 12 times 2 is, and square whatever 84 times 2 squared is, and square root the sum of those squares, and that would get you the magnitude. And for the direction, you would just use inverse tangent of the y component over the x component if you want the angle with the x, or the x component over the y component if you want the angle made with the y-axis, whatever you prefer there, but chances are you'll go for the one with the x-axis because that's what we're used to doing. Okay, that wasn't too bad. Next up, we've got the velocity of a particle moving in the xy plane is given by, so this time they give us the velocity function. Let's do it in a different color. I don't think I've used pink yet today. So it says the velocity of a particle moving in the xy plane is given by v equals, sometimes they write v of t, sometimes they just write v. Either way, it means v of t. I'll just write v of t anyway, even though they didn't do so in the book, just so that it's extra clear. V is equal to 6t minus 4t squared, 6t minus 4t squared in the I hat direction, or in the x direction, in other words, plus 8j hat, plus 8j hat. Okay, assume t is greater than 0. Part A, what is the acceleration when t equals 3? So first question is, what is a of 3? Second question, when, if ever, is the acceleration 0? When is a of t equal to 0? It needs to be 0 in both the x and y components. and then C, when, if ever, is the velocity 0? So third question is, when is v of t equal to 0? And the fourth question, when, if ever, does the speed equal 10 meters per second? When is, speed is the magnitude of the instantaneous velocity. When is magnitude of v of t equal to 10 meters per second? And again, it's possible for some of these to not have a solution. It said when, if ever. Okay, acceleration at time 3, that's not too hard to do. Same thing we did in the previous problem, in fact. Just take the derivative of velocity with respect to time, and you've got acceleration as a function of time. So derivative of the x component with time is going to be, let's see, d v of t dt is equal to 6 minus, that's going to be 8t in the I hat direction, plus 0 in the j hat direction. The derivative of a constant, the derivative of 8, is 0. 8 doesn't change no matter how much time passes. So yeah, the acceleration is purely in the x direction here. So what's the acceleration at time 3? You plug in 3, 6 minus 8 times 3, 6 minus 24 is negative 18 meters per second squared. Are those the correct units for this problem? Yeah, all the units they gave are in meters and seconds. You don't see it, but I could have written them down, but I didn't bother to. It was actually written as, so the 6 is written with units of meters per second squared, and then the minus 4 over here is written in meters per seconds cubed. And that makes sense because meters per second squared times t in seconds gives you meters per second. Those are velocity units. And then meters per second cubed times time squared, that would also reduce to meters per second. So the units do actually check out. But yeah, units are in meters and seconds, in case you were concerned about that. They were actually written in the equation. I just didn't bother copying them over because I don't usually write my units in my equations anyway. Part B, when, if ever, is the acceleration 0? When, if ever, is the acceleration 0? Well, just take your acceleration over here. I should have also written this is a of t, and set it equal to 0. And see if there's a solution for it. The acceleration is 0 when all of its components are 0. Well, the y component and the z component, which wasn't even mentioned in this problem, are already both 0. Is it ever possible for the x component to also be 0? Yes, because you can just set 6 minus 8t equal to 0, and that gives you at time 6 over 8, right? When t is equal to 6/8 or 3/4 or 0.75. So at t equals 0.75 seconds, the acceleration would be 0. It would be 0 in the x component and in the y and z component. A vector is only 0 when all of its components are 0. That probably goes without saying, but just in case you didn't know, now you do. When is v of t equal to 0? Well, v of t has an x component, which I guess we could solve for a time when this is 0, plus a y component that is constant. Oh, the y component will always be 8. It will never be 0, so there is no way to get all of the components to be 0. So for this one, never. There is never a time where v of t is equal to 0 because it's got a constant vertical component that is not 0. And then when is the magnitude of the velocity equal to 10? Okay, well, magnitude of a vector is just Pythagorean theorem, square root of the sum of squares. Equals the square root of six t minus 4t squared for the x component plus for the y component it looks like it's going to be 8 squared. So yeah, first component squared plus second component squared, and if there was a third component, you would do plus third component squared. So we need to set this equal to 10. If I square both sides, that just means 100 equals whatever this thing is when squared. Oh God. I don't actually want to square this. I'm going to leave it as is because I see something here. 100 minus 64 is 36. 100 minus 64 is 36. And now if I square root both sides of this, then I get 6. Well, plus or minus 6 really, is equal to 6t minus 4t squared. So if I move these over to the right hand side, then I get 0 equals 4t squared minus 6t plus or minus 6. Let me see, do I actually need the plus or minus here? Let me think about this for a second. So that expression squared has to equal 36. T can only ever be positive. Right, they did say assume t is greater than 0. Well, I mean, the bottom line is we've got a quadratic function on our hands. That's the bottom line. So let me see if, can we actually just simplify this by factoring? Can I just do 0 equals, let's see. Well, I can factor out a 2. And then that leaves me with 2t squared minus 3t plus or minus 3. And then divide both sides by 2 so that 2 out front cancels out. Should be factorable. Factors of 6 that add up to -3, or factors of -6 that add up to -3. No, actually. No, it doesn't look like it. We might actually have to do a quadratic formula. Okay. So we've got -3 is +3 plus or minus the square root of -3 squared minus 4 times 2 times plus or minus 3 all over 2 times 2. So that's going to be 9. And then 4 times 2 times positive 3 isn't going to work because that's going to be minus 24. 9 minus 24 is a negative. We can't have a negative under the square root. So it's definitely not positive 3. It has to be the negative 3. Yeah, it has to be the minus. So 9 minus negative 24, that's positive 33. So yeah, it'll be 3 plus or minus square root of 33 all over 4 are your possibilities for t. And then actually we can eliminate the minus, because if I do 3 minus the square root of 33, square root of 33 is going to be somewhere between the square root of 25 and the square root of 36. It's going to be somewhere between 5 and 6. And if I do 3 minus something between 5 and 6, I'm going to get a negative time. And they said assume the time is greater than 0. So I can already eliminate the minus over here. It's 3 plus the square root of 33 over 4. And then you can plug that into your calculator or leave it as is, whatever you prefer. But that would be the time when the magnitude of the velocity, when the speed is 10 meters per second. All right. So what this problem teaches us is that algebra still matters. Look at how much algebra was done after the calculus step was taken care of. Calculus is usually just the opening step for a lot of calculus problems, and the rest of it is algebra. So if you have to choose whether to invest in your algebra skills or your calculus skills, prioritize your algebra skills first. Can't get far in calculus without algebra, and besides, there aren't that many calculus-based questions on the AP exam anyway. It's quite possible, depending on your luck and how well you know all the other stuff in the course, it's quite possible to still get a 5 without knowing any calculus at all. I wouldn't recommend it, but it's better than the shotgun approach of trying to just half learn calculus to the neglect of algebra. That probably won't work out too well. What does this next one say? A particle is moving in the xy plane with velocity v of t equals vx of t I hat plus vy of t j hat, and acceleration ax of t I hat plus ay of t j hat. By taking the appropriate derivative, show that the magnitude of v can be constant only if ax vx plus ax vy is equal to 0. I think that one might actually require implicit differentiation, but let me write it down and think about it first. If it requires implicit differentiation, you don't need to know how to do that. Not for the AP Physics exam, at least. For AP Calculus, oh, you definitely need to know your implicit differentiation. So we've got the velocity, just a generic velocity function and a generic acceleration function, and show that the magnitude of v can be constant only if ax times vx plus ay times vy equals 0. So magnitude is constant. Okay, well, at the very least, I want the start of this problem. I think it might require implicit differentiation to finish it, but at least starting it contains an important idea here. So we've got v of t is simply some x component plus some y component, and acceleration is also being written as some x component plus some y component, or it could be minus if one of these components is negative. We don't know either way. So it's asking us to show that the magnitude of v can be constant only if ax vx plus ay vy equals 0. So the question is, under what conditions is the magnitude of v constant? That is the question. When is magnitude of v of t constant? Well, for something to be constant, what does that mean in calculus terms? In calculus terms, if something is constant, then its derivative must be 0. That's the main takeaway from this. If you're looking for when something is constant, especially if it involves a variable, and I forgot to close my parenthesis there, when you have some expression and you want it to be constant, when you have an expression that contains multiple terms, which magnitude definitely contains multiple terms, it's Pythagorean theorem, it's the square root of the sum of squares like we did earlier. When you're trying to solve for when something that contains a bunch of variables in it is constant, you are looking for where its derivative equals 0. So we want to set the derivative of the magnitude equal to 0. Let's see what that would look like, and if it requires implicit differentiation, I'm probably just going to leave it alone. Then again, I think it might actually be as simple as the one that I did show off earlier. Yeah, I think it's actually going to be the same as this, pretty much. So if we're looking for when the magnitude is constant, then we're also looking for when the square of the magnitude is constant. So here's the problem. If I try to take v of t, that's going to be the magnitude of v of t, that's going to be the square root of vx squared plus vy squared. And yes, they're actually vx of t and vy of t, but just for the sake of getting it written down faster, I'm leaving out the t in the parentheses for a minute. So if I want to take this derivative, then I'm taking the derivative of a square root, which you can do. You can rewrite this as vx squared plus vy squared in parentheses, and then raise it to the 1/2 power, and then do power rule on that. You could do it that way, but there's an easier way if you know your implicit differentiation. If I just square both sides of this, and solve this by implicit differentiation, if the magnitude of the velocity is constant, if I'm looking for where the derivative of this is equal to 0, then that's also where the derivative of its square must be equal to 0. If the rate of change in something is 0, then the rate of change of its square must also be 0. Actually, wait, is that true though? Let me think this through. If something has a rate of change of 0, then the square of that thing must also have a rate of change of 0. I mean, it sounds right to me, but I feel like I'm missing some sort of condition for that. Yeah, I'm not entirely sure I want to commit to that statement just yet. But yeah, if you don't know your implicit differentiation, then good luck doing this. It's doable. It's just... Well, actually, even here, you would still need to do implicit differentiation because you're going to be chain ruling. So, yeah, implicit differentiation is unavoidable. So I would just do the same thing I did with that other problem over here. And just do the derivative of this. It'll pretty much end up looking like this, except for this problem. I was looking for where it's less than 0, and in this problem I would just be setting it equal to 0. And the expression that you should get, for those of you who know your implicit differentiation and really want to try this, the expression that you should get is ax vx plus ay vy equals 0. That is what you should be getting if you're curious and you want to do that on your own, but I'm ready to move on. I already got the important bit out of this, which is if you're solving for when something is constant, one option to consider is solving for when its derivative is 0. Now let's take a look and see what else I have lined up. Okay, here we have a graph to analyze. We've already spent almost an hour and a half on kinematics alone. So much for getting everything done in one stream. I don't know if that's going to be possible. Well, I mean, to be fair, some of the other topics might be shorter. So it says we've got a graph of x versus t in the figure. I will copy it. Wait, I did that wrong. There's the t and there's the x. Great. Brain is malfunctioning already. Okay, so graph starts somewhere up here at, they called it point O. And then from there to point A, it looks actually mostly straight. And then it curves to point B, and then it goes straight to point C, and then it curves down to point D, like that. And yeah, that's the graph of x versus t for a particle in straight line motion. It says, state for each interval whether the velocity is positive, negative, or 0. And this is, again, a one-dimensional motion, so positive means in the positive x direction, negative means in the negative x direction. Those are the only two directions here. This is representing one-dimensional motion. So it says, state for each interval whether the velocity is positive, negative, or 0, and whether the acceleration is positive, negative, or 0. Really, you should be able to do this even without calculus if you stare at the graph long enough and think about it. But with calculus, we know a little bit more about what to look for. So velocity is the first thing they want, and velocity on a position versus time graph is just slope of the tangent line. So for this first interval from O to A, velocity is positive, right? This thing is going upward. From A to B, it's also positive. From B to C, I didn't draw it well, but it's supposed to be a horizontal line. So that would be 0. And then from C to D, it looks like it goes downward, so that's a negative velocity. So first derivative of a graph is the slope of the tangent line at any given point on that graph. Second derivative, I don't think I talked about this last time, but the second derivative is the concavity. Second derivative is concavity. Second derivative is concavity on a graph. Concavity. What on earth does that even mean? What on earth does that even mean? Concavity just means, is it curving up or down like this? Some people say up like a cup and down like a frown. This means concave up or positive concavity. This means concave down or negative concavity. And it doesn't have to be this full U shape. It can be this by itself is concave up, or this by itself is considered concave up, and this segment by itself is considered concave down, and so is this over here. So yeah, you don't have to have like a full U shape or upside down U shape in order to have concavity. You just have to have some sort of curvature and some sort of direction to that curvature. So straight lines have 0 concavity. So acceleration, which is the second derivative of position, it's the derivative of the derivative of position. Here, concavity is 0 because from O to A, that's a straight line. So acceleration should be 0 there. That's just a constant velocity. Over here, it curves downward. That's concave down. So that's going to be a negative acceleration. Here it's a straight horizontal. Straight lines, whether they're horizontal or otherwise, have 0 concavity, so there's no acceleration here. And then from C to D, it's concave up, so here there would be positive acceleration. And that's pretty much it. There's a second part that says, from the curve, is there any interval over which the acceleration is obviously not constant? And it says, ignore the behavior at the endpoints of the intervals. Is there any place where the where the acceleration rather is obviously not constant? Well, we know the acceleration from A to B is negative, but we don't know if it's a constant negative or not. And from C to D, same thing. We don't actually know. The acceleration could be constant or it could be variable. We can't really tell. It's not obvious over here. What would make it obvious was if we had a graph which we knew was higher than second degree. Because if your position versus time can be expressed as a quadratic function of time, that's constant acceleration. But if position versus time is anything higher than quadratic, then we would have an obvious variable acceleration. So if it looks like a cubic function, then that would tell me the acceleration isn't constant. But we can't tell, like from A to B, that small bit of curve, or from C to D for that matter. The C to D over here, it looks like it's a segment of some sort of quadratic curve. It could also be a segment of some sort of fourth degree curve. It could be part of a fourth degree polynomial for all we know, but it's not obvious. That's the key word there. They were asking, is there any interval over which the acceleration is obviously not constant? And the answer for that is no. It's possible, but it's not obvious. We don't know for sure. With polynomials, you need more than just 2 points to determine the degree of a polynomial, as you may know. You have to look at several turning points in here. Since it's cut up into all these different segments, we can't really say for sure what the overall behavior of the graph looks like. Sounds like a lot of people are driving motorcycles outside right now. I mean, it has gotten warm enough for that. There's a second question that's basically the same thing, analyzing a graph. We can skip that. Let's see what we have over here. I highlighted this one. Says the position of an object moving in a straight line is given by x equals at plus bt squared plus ct cubed, where a, b, and c are 3, -4, and 1 respectively. What's the position of the object at each of those times? What's the displacement between those different time intervals? And what's the average velocity? Okay, that's not a calculus question. What about this one? Position of a particle moving along the x-axis is given by 9.75 plus 1.5 t cubed. Consider the time interval from t equals 2 to t equals 3 and calculate average velocity, instantaneous velocity at time 2, instantaneous velocity at time 3, and the instantaneous velocity at time 2.5, and the instantaneous velocity when the particle is midway between its positions at time 2 and time 3. It seems simple enough. I feel like with the examples we have done, we don't need that one. So I think I'm just going to move on. Let's see what we have next. So I guess it's time to talk about air resistance a little bit. Well, actually, let's do some stuff with force. Yeah, let me take a look and see, because according to my notes, there was this force question to look at first before going back and doing a little bit more kinematics. Let me see what that was all about. So it was question number 15 here. What was it? Okay, we would need to talk about air resistance first for that. Let me see, and the next thing on my list was over here. What kinds of questions do we have here? And I think this one combines both kinematics and force. Okay, yeah, so let's talk a little bit about air resistance. Let's take a look at just a classic air resistance question. Let's say that we have the drag force on an object is just going to be some linear air resistance is just going to be negative bv, where v is the speed, the magnitude of the velocity of the object, and I guess the direction of the drag force is going to be opposite to the direction of the velocity, as the case typically is for air resistance, and by typically I mean always. Resistance is a force that opposes motion. Air resistance is a force that opposes the direction of an object's motion. So let's say that an object is dropped from rest. Let's say that I have an object and it's dropped from rest from a very, very high building. And it's just allowed to fall. So dropped from rest. What are the forces acting on it if air resistance is not negligible? Well, there's going to be a downward force on it of mg. And there's going to be some upward force on it, which is going to be the drag force, or air resistance force, whatever you want to call it. And if I wanted to write the net force equation for this thing, then I would say net force on the object, which equals its mass times its acceleration, equals, I'm going to use down as my positive direction here. I'm going to say down as the positive direction for this problem. And I'm going to do mg minus my force upward minus the magnitude of this force would be bv. mg minus bv. Don't worry about the negative sign in here. Just like the way I've been doing spring force whenever it showed up in problems, just focus on magnitude and determine direction based on your definition of which way is positive and which way is negative. Don't worry about the negative sign that's in the equation itself. So in my case, mg is in the positive direction, while bv is in the negative direction. So if I rewrite the acceleration as the derivative of velocity, then I now have a differential equation. That I can solve for velocity as a function of time. Let's make some adjustments to this first. I'm going to divide by m. So I get dv dt equals g minus b over m v. And this is a separable differential equation. I can group my v's with my dv's, and I don't have any t's, so that's perfect. I can just keep my dt out there by itself. So I'm going to quote unquote multiply the dt over to the right hand side, and I'm going to divide this whole entire thing over to the left. So I'm going to get 1 over g minus b over m v dv equals the dt. And if you don't like the dt being on its own, you can write a 1 in front of it if you like. But now what we can do is we can take the integral on both sides. The problem might ask you to just set up but do not solve a differential equation, in which case you would just stop right here. But if they do ask you to continue to solve it, it's not too terrible. So here we've got 1 over constant minus constant times my variable, which is v. So essentially 1 over something involving my variable to the first power. If you look at your formula sheet, 1 over the variable integrates to something having to do with the natural log. It integrates to something having to do with the natural log. So we'll make a u substitution here, and see how that works out. So integral of 1 over g minus b over m v dv equals the integral of dt. So I'm going to make a u substitution here. I'm going to do u equals g minus b over m times v, and then if I take the derivative of u with respect to v, that gives me du dv equals, well, the derivative of a constant g is 0, and then derivative of negative b over m times v is just going to be negative b over m. Derivative of a constant times my variable to the first power is just whatever that constant was in front of my variable. I'm going to move the dv over to the right-hand side, and actually, yeah, I'm going to move it over to the right-hand side and multiply by negative m over b to the left-hand side. So I get negative m over b du is equal to dv. This is just another way that you can do your u substitution. I can substitute my dv with negative m over b du. If you didn't like the method that I did last time where you had to make your du by, if you didn't like the method of, let's see, so it would have been just multiply the dv, and you would have had, so here's the other method I showed last time, du equals negative b over m dv, and then you would have to look in your integral and make a negative b over m dv by multiplying and dividing by negative b over m, so that overall you're multiplying by 1. If you didn't like that approach, this is an alternative approach that's a little bit less of a headache, where you just solve for the dv itself and then plug in whatever you get in this original integral. So that's also an approach you can take. So yeah, rewriting this integral, it's going to be integral of 1 over g minus b over m times v. We're substituting that with a u. And then the dv is going to be negative m over b du. I'll write the negative m over b outside of the integral. Since it's a constant, I can do that. And then write the du inside the integral where it belongs. And then the integral of 1 over u du, that's the natural log of u. So I get negative m over b natural log of the absolute value of u, and the u is going to be g minus b over mv. And that's going to equal the integral of dt is just going to be t plus a constant. I could have done the plus c over on the left-hand side if I wanted to, but wherever you put it, or you could have done it on both sides. We went over it last time. If I did a plus c1 on the left side and a plus c2 on the right side, I could have subtracted one of them from the other to create a new plus c3, or I think I called it c star or something like that. So really you only need the constant on one side of the equation, and I prefer to keep it on this right hand side because there's already a lot going on this left hand side. Okay, so now what I want to do is multiply by negative b over m in order to cancel this out. So I get natural log of g minus b over m v equals negative b over mt plus negative b over m times some arbitrary constant is some other arbitrary constant. I will call that c star. So c star is equal to this c times negative b over m. And then if I exponentiate both sides, if I do e to the left-hand side equals e to the right-hand side, I get e to the natural log cancels out, and I'm just left with g minus b over m v of t, to be more specific, equals e to the negative b over m t plus c star. And this can be rewritten, we saw this last time, I believe, g minus b over m v of t equals, this just becomes e to the negative b over mt plus e, or rather times e to the c star. I'll write e to the c star first, actually. Times e to the negative b over m times t. And then e to a constant is yet another constant. I guess I will call that, let's call it c0. c0 e to the negative b over m times t equals g minus b over m times v of t, and you can solve for v of t over here. Just subtract the g and then multiply by negative m over b. I guess I'll do that up here. Yeah, I think this would probably be a setup but do not solve problem considering all the steps involved here. So we would have subtract g, multiply by negative m over b. So that's going to be c0 e to the negative b over m t minus g, and then multiply by negative m over b. So that's going to become negative m over b of this, and then plus multiply that by m over b, and that will be my v of t function. And then solving for c0 now, do we have an initial value? We should, because if this thing is dropped from rest, then we know v of 0 equals 0. So I can just do 0 equals negative m over b times c0 times e to the negative b over m times, well, t is going to be 0, right? v of 0 is what it is. v of 0 equals 0, so 0 equals, when you plug in 0 for time, this just becomes e to the 0, which is 1. And then plus g m over b, or mg over b, rather, is another way of looking at it. And that leaves me with what? mg over b minus mc0 over b equals 0. So if I add this to both sides, mc0 over b equals mg over b. Ah, c0 is equal to g. This implies that c0 is equal to g. Okay, so this is negative mg over b. That means I can factor out mg over b from these two terms. Ooh. Let's switch colors here and see what we end up with. So if we continue up here, I guess I did this whole problem from right to left, huh? Oh well. If we continue, we get v of t equals, so I'm going to take this negative term and move it to the right-hand side and move this to the left-hand side. So I've got mg over b, that was this part, and then minus m, we said c0 is g over b, e to the negative b over m times t. If I factor out the mg over b, then I get 1 minus e to the negative b over m t. I probably need to write that b over mt a little bit better because, yeah, let me rewrite it. V of t equals mg over b times 1 minus e to the negative b over m times t. There we go. And if we look at the graph of this, here's what we will find. Of course, I've defined down to be the positive direction, so since the velocity is going to be gained in the downward direction on the graph of this, it should show up positive, just because I've decided that down is positive for this problem. So what we have is, let's see, mg over b times 1 minus e to the negative b over mt. Well, an exponential graph in general, e to the x looks like this, right? It just kind of curves upward like that. E to the negative x is flipping that horizontally, so that would be starting up high and curving downward. So that's e to the negative x. And then negative e to the negative x is flipping that over vertically. So that would be, so take this and flip it over vertically, and it should look like this. And the exponential function has a horizontal asymptote, so it's going to start at some sort of value. Well, we know it starts at velocity equals 0, and it's going to asymptotically approach some sort of limiting value. It's going to approach some sort of horizontal line that it never quite touches. So that's your v versus t graph. And we actually know what this velocity is because we talked about it before we knew any calculus. This is the terminal velocity. This is v equals v terminal. V terminal. Or v term, as I think I may have once called it. This is the velocity where the drag force is completely equal to the gravitational force, so that the net acceleration ends up being 0 from that point onward. It never actually fully gets there, but it gets awfully close to that value. And if we try and look for what happens when a lot of time passes, e to the negative whatever b over m is, times a very, very large amount of time, e to a very large negative, that approaches 0. So you're left with mg over b times 1 minus very nearly 0. So v terminal, this dotted line should be at v equals mg over b. And is that right? Well, if we set the drag force equal to the gravitational force, if we set BV equal to mg, BV terminal, then yeah, just divide by B and there you go. mg over B is indeed the right horizontal asymptote to be getting. So it agrees with what we knew before we knew any calculus. So whenever you see linear air resistance, expect some sort of exponential function. Whenever you see linear air resistance, just expect to see some sort of exponential function, because that's kind of what air resistance does. It makes your velocity decay over time until it approaches some sort of limiting value. Or in this case, it's not a decay so much as a growth. It's just a growth that slows down to some limiting value. If you started with some sort of velocity greater than this terminal velocity, you could have had, I didn't leave enough space for it, but if I had space for this graph to start further up, if I started with some velocity, if I started at the top of a building and I threw something down forcefully so that it started faster than the terminal velocity, that would just mean that the drag force starts out bigger than the gravitational force, and there would be a net slowdown until eventually it asymptotically approaches the terminal velocity from the opposite side. It would start somewhere up here and it would gradually slow down like this. So either way, whether you start from below or above the terminal velocity, you approach it asymptotically. Either way, that is what you should expect to see if you end up doing one of these air resistance calculations. If you're not getting this, then you probably made a mistake somewhere and you need to backtrack through your steps and see where things went wrong, if things went wrong. Anything else I need to comment on for this? Let me think here. I feel like there was one more thing I wanted to say, but I'm blanking on it. Yeah, I've got nothing, but if I remember something later that I forgot to bring up here, then we can go back to it. Let's have a look now at what else I have listed for example problems. So they said in this problem over here, what did they say? Was it even? Oh, yeah, and it is related to air resistance. How about that? And just more conceptual than anything else, it looks like. It says a parachutist is in free fall before opening her chute. The net force on her has magnitude F and is directed down. This net force is somewhat less than her weight, W, because of air friction. Then she opens up her chute. At the instant after her chute fully inflates, the net force on her is greater than F and still directed down, less than F and still directed down, 0, or directed upward but could be more or less than F. Okay, so really conceptual. We don't have to do any calculus here, but we do need to understand how air resistance works. So she's in free fall before opening her chute. Net force on her has a magnitude F and is directed downward, somewhat less than her weight because of air friction. Okay, yeah, that makes sense. So you've got the mg downward and subtract from it whatever drag force you have, and the net force is still downward, but less than the full mg. Okay, so far so good. Then she opens her chute. At the instant after her chute fully inflates, the net force on her is... Okay, so at some point before reaching terminal velocity, parachute is opened. What that does is that increases this B. That increases like the surface area that's catching air particles, which increases the amount of air resistance encountered per meter per second of velocity that you might have. So it increases your air resistance. So if air resistance is increased pretty much instantly, at the instant after her chute fully inflates, the net force on her becomes what? Greater than what it was before and still directed down? Less than what it was before and still directed down? 0, or directed upward but could be more or less than the original net force. So will the net force increase, decrease, become 0, or end up being upward? Well, in order for the net force to be upward, you would need the drag force to become greater than the person's weight. And that's possible if they reach a high enough speed first. So let me see here. So they would have to be... So B1V, we know that the original B1V, is less than mg because they're not at terminal velocity yet. And then you come with B2V, which for that same V, it depends on how much bigger B2 is compared to B1. Because, so V would be, let's see, V is less than mg over, mg over B1, is what we can conclude from the first scenario. For the second scenario, B2 times V B2 times V, is it less than, greater than, or equal to mg? We don't really have enough information to say. But probably B2V is still less than mg. This is most likely. Whatever V is, it's less than mg over B1. So is V also less than mg over B2? I guess it would depend on how much greater B2 is than B1, and it would depend on what V is. Yeah, I don't really like this question. They could have given us a little bit more information here. Or they could have given us an option that says not enough information, which is what I would have chosen if it was an option. Is the magnitude of the force greater and still directed down? No way that the net force would increase. The force opposing mg, even if this drag force did suddenly become greater than mg, even if that were the case, it's highly unlikely that it would become so much greater than mg that the magnitude is lowered. So we can definitely eliminate choice A. It's definitely not greater than the original magnitude. Very unlikely for that to be the case. B seems to be the best answer, less than the original net force and still directed down. That's probably the best answer we have. Choice C, 0, possible, but it would have to be super perfect. Like the parachutist would have to have super precise timing to make that work. So I'm going to say no because it's very unlikely. And D, directed upward, but could be more or less. Possible, but again, not likely. It would require a very large B2 to B1 ratio for that to work. And also it would depend on how fast, it would depend on what V is the moment the parachute is opened. If the parachute was opened when the net force was just 0, then that would be a whole nother story, but that's not what the problem describes. The problem describes having some net force downward, which means the person was still accelerating downward before the parachute was opened. Yeah, interesting problem to think about, but I don't like the answer choices given, considering how many open questions there still are, but it looks like B is the best answer we can give. The magnitude of the net force is decreased after the parachute is opened and is still directed downward. That is the most likely scenario. Sometimes this book, with the way it words its questions, I don't even know. Okay, let's move over to some more problems on this other page. What did I highlight here? Okay, so for this one, we have, it looks like another multiple choice one. What does it say? So it says an object moves with a constant acceleration a. Which of the following expressions are also constant? Let me go ahead and, actually, we can squeeze it in down there. So it says an object moves with constant acceleration a, and we've got 4 answer choices, and it's asking which of these are also constant. So choice A says derivative of the magnitude of velocity with respect to time. Choice B is the magnitude of the derivative of velocity with respect to time. Choice C is the derivative of the square of the speed with respect to time. And part D is derivative of the velocity, derivative, that's a parenthesis, derivative of the velocity over its magnitude. With respect to time. So those are the 4 possibilities. And again, we are told acceleration is constant. So which of these 4 would also be constant? This is all about understanding notation and understanding the meaning of your derivative. Understanding the meaning of the derivative is the key to this. And of course, knowing your physics as well. So let's see. First of all, derivative of the magnitude of the velocity with respect to time. That is, the rate of change of the speed. Is that constant when the acceleration is constant? Well, you might be tempted to say yes, but that's because you're only thinking in one dimension. You might be tempted to say yes, but that's only because you're thinking in one dimension. Because what if the object is moving like this, has a velocity this way, and the constant acceleration is, let's say, this way? Well, then that's going to add some velocity to it in that direction, and then I guess after a certain amount of time passes, let's say after 1 second passes, you get one multiple of this acceleration added tail to tip over here, and then the new velocity becomes 1 second later, the velocity becomes this. So the magnitude increases by some amount over here. And then in the next second, you add one more copy of this. And now the magnitude of the velocity turns into this. I don't think my drawing is too clear, especially with the orange. Let me try green. And then the magnitude of the velocity in that second becomes this. So yeah, is the increase from this blue to this first orange the same as the increase from this orange to now this green vector that I've drawn? I wouldn't count on that. I would not count on that. If this was all in a straight line, sure, that would be the case, but the acceleration is not in the same direction as the velocity, so A cannot be correct. Okay, what about the magnitude of the derivative of velocity with respect to time? Well, the derivative of velocity with respect to time is, by definition, the acceleration, and if the acceleration is constant, then its magnitude must also be constant. If acceleration is constant, its magnitude and direction are both constant. So this appears to be a correct answer. But it did say which of the following expressions are also constant. So there could be more than one correct answer here. Okay, what about derivative of the square of the speed with respect to time? What about the derivative of the square of the speed with respect to time? This is the same as the square of the magnitude. So v of t magnitude squared, that's equal to, let's think about it in 2 dimensions. It should still work fine in 3 dimensions as well. That would be vx squared plus vy squared. So if there is a constant acceleration, then a certain amount is being added to x and y, maybe just one or the other, or maybe to both. There's some sort of addition to x and y, so we would do, let's see, I guess I would say, so this is before the acceleration is applied and after the acceleration is applied. Vx increases by, I guess we'll call it delta Vx, and then Vy squared Vy is going to increase by delta Vy. And then if we square that, let's see. So 1 second, you add 1 delta Vx and 1 delta Vy, and that increases the magnitude of V squared by some amount, but that amount is going to, the net increase is going to be less significant after a long amount of time. When Vx and Vy get really, really big after some long amount of time, adding the same amount of delta Vx and delta Vy after a very long time isn't going to change Vx plus delta Vx by very much. So let's say for example you had, let's say for example Vx and Vy started at 3 and 3, or 3 and 4. Yeah, let's do 3 and 4. So let's say Vx and Vy started off as 3 and 4. So you started with magnitude of V of t squared equals 3 squared plus 4 squared, for example. And let's say the acceleration is, let's say it's 1 in the x direction and 2 in the y direction every second. So 1 second later, so after 1 second, you get 3 plus 1 squared and 4 plus 2 squared. So you went from, let's see, so you went from 9 plus 16, you went from 25 to, this is 4 squared, which is 16, plus 6 squared, which is 36, 16 plus 36. So we went from 25 to 16 plus 36 would be 52. So you went from 25 to 52. And then 1 second after that, so you go from 3 plus 1 squared to 3 plus 2 times 1, 3 plus 2 squared. And then for the y, if its acceleration is 2, then after 2 seconds of an acceleration of 2, that would be 4. That's 3 plus 2 is 5 squared plus 8 squared, 25 plus 64 is 79, right? No, 89. 25 plus 64, yeah, 89. Okay, so from 25 to 52, the increase over the course of 1 second was 27. The increase in the magnitude of the speed squared was 27. And then from 52 to 89, the increase is, looks like 37. The increase from 52 to 89 is 37. What about 1 second after that? I mean, we can already see from here that it's not a constant rate of change if in the same amount of time you're getting different amounts of change. So even without doing any calculus, we can answer this. So after 3 seconds, that's 3 plus, this was a 1 for every second, so 3 squared plus, that's going to be 4 plus, let's see, so that would be 6, right? We said it was 2 for every second in the y direction. That would be 9 squared is 81, plus 10 squared is 100, so that's 181. Ah, so yeah, what's more significant, I guess, is how much speed you built up in the previous second. The fact that you're adding 1 to the x velocity and 2 to the y velocity every time is less relevant than how fast you were in the previous second. So yeah, you can see 25 to 52 is a 27 change, 52 to 89 is a change of 37, 89 to 181 is a change of almost 100, and is a change of 92. So yeah, the rate of change per second is actually increasing, it looks like. So C is definitely wrong. And then D. So D is interesting. We didn't really talk about this, but the velocity divided by its magnitude. What is that? A vector divided by its own magnitude. The only thing you achieve by dividing a vector by its own magnitude is you reduce its magnitude to 1. So the only information left in this, really, is its direction. When you divide a vector by its magnitude, all you get is a vector of 1 that has the same direction as the original vector. So what this is really telling you is we are locking the magnitude of this thing to 1, and what we're really differentiating, what's really changing with respect to time, if the magnitude is being locked to 1, what's really changing, if there is a derivative here at all, is the direction. So they're asking, does the direction of the velocity is the direction of the velocity constant over time? Or rather, is the change in the direction of the velocity constant over time? And that would also be a no, because if we, just like I said for part A, if we consider that the velocity and the acceleration were not in the same direction, if I add some velocity after some amount of time has passed and I'm accelerating in this direction, if I add some velocity and I get this new velocity over here, there's a change in direction, and then if I wait for 1 more second to pass and I add 1 more acceleration times time to this, then the direction changes again. Over a long period of time, the amount of directional change, if we measure it in like degrees, for example, by how many degrees does the direction of the velocity change, over time the direction of the velocity will get closer and closer to, but never quite match, the direction of the acceleration. If you were to just do this process repeatedly, just approximate it by doing it 1 second's worth of acceleration at a time, you would eventually get a vector that approaches but doesn't quite match the direction of the acceleration. So the amount of change in direction per unit time, that's also not constant. So the only correct choice here is B. Yes, we answered it quite a while ago, but I felt like in this question, thinking about the other answer choices is a very worthwhile endeavor. It's one of my favorite questions to ask students every year for Physics C. But now we can finally move on to another one. Let me see what else we have here, and I think I'm going to have to start getting picky because we're almost 2.5 hours in already. What did I list here? What does this one say? Now we can skip that one. What about that one? Yeah, that one we can also skip. And then this one, a parachutist jumps out of a plane. Okay, this is similar to that other one from earlier. So it says a parachutist jumps out of a plane. He falls freely for some time. That means, translation, that they've been falling long enough that they've reached terminal velocity. So he falls freely for some time and then opens his chute. Shortly after his chute inflates, the parachutist will A, keep falling but quickly slow down. B, momentarily stop, then start falling again but more slowly. C, suddenly shoots upward and then starts falling again but more slowly. Or choice D, suddenly shoots upward and then starts falling again, eventually acquiring the same speed as before the chute opened. So those are our answer choices. Let me write them down on a new sheet. So we have a parachutist who reaches terminal velocity. So they have a drag force acting on them, and they've got the force of gravity, and so at some point they reach B1 times V is equal to mg. So at some point they reach this, they reach V equals mg over B1, and then they pull open their parachute and their B increases from B1 to B2, essentially. So at another moment in time, their drag force increases. I guess we'll call this drag force 1, and we'll call this drag force 2. So at this point, they have some upward acceleration, at least temporarily. They have some upward acceleration. And the answer choices were keeps falling but quickly slows down. So A, falls but slows down. B, momentarily stops, then starts falling again but more slowly. B, stops, then falls slower, is how I will summarize it. Maybe I shouldn't have picked so many multiple choice questions. C, suddenly shoots upward, then starts falling again, but more slowly. So C, rises, then falls slower. And D, suddenly shoots upward and then starts falling again, eventually acquiring the same speed as before the chute opened. So rises, then falls at previous speed. So those are the four possibilities. Well, we know that their new terminal velocity has to be, so sometime after this, force drag 2 has to decrease because they're going to slow down, so the drag force is going to decrease with them until it's equal to mg again. And then that's going to be, so I guess this would be BV1 actually, and V1 equals mg over B1. And then over here we get B2 times V2 is equal to mg. So V2 equals mg over B2. So yeah, your possibilities are these four. So let's consider these two first. The claims that the person rises and then falls. That is very, very unlikely because in order for them to rise, the drag force acting up on them, in fact, I think it's impossible. The drag force acting up on them would not only have to be greater than mg, but it would have to be so much greater than mg that it gets rid of all the downward velocity that they already have and then give them some upward velocity on top of that. But if it got rid of all the downward velocity, then that upward force would disappear because it depends on velocity. So it could never possibly get to that point. It could never possibly get to that point. So C and D are impossible. It is impossible to rise because that would mean that they need to decelerate to 0 first and then accelerate to an upward velocity. But decelerating to 0 eliminates the drag force to begin with. And there's no other force that could cause them to move upward. So C and D we can eliminate right off the bat. Stops, then falls slower would be the next suspect over here. So is it possible for them to stop and then fall slower? Well, if the drag force acting up on them is high enough to get them to a stop, then that drag force would disappear, leaving them with the downward acceleration due to gravity for a moment in time. But does it even get to that point? Because in order to slow down to 0, while they're slowing down, that upward drag force is decreasing anyway. So before it even manages to decrease all the way to 0, it would become so small that it would be less than mg, in which case you wouldn't have an upward acceleration anymore. So B is also not possible. So by process of elimination, it has to be A. They fall, but they slow down. And the reason they slow down is because now they've got a bigger B2, so their V2 is going to be equal to the same mg divided by a bigger number than it was before. So yeah, V2 is less than V1. Not really a calculus question, but air resistance nonetheless. I mean, I guess you could do the calculus if you really, really wanted to figure out exactly what happens to this person, but that's too much of a headache. We can just do this using concepts. And I guess that's the other important thing to take away from all this is, like I said last time, don't get too over-eager to use calculus on every little problem. Make sure you actually can tell when the calculus is actually necessary. Don't bring out the power tools for problems that don't require power tools. Now let's see some more proper exercises with numbers in them. So I have, what do we have here? We've got an ice boat sails across the surface of a frozen lake with constant acceleration produced by the wind. At a certain instant, its velocity is 6.3 I hat minus 8.42 J hat in meters per second. 3 seconds later, the boat is instantaneously at rest. What is its acceleration during this interval? That's easy to do. It's really just an exercise in working with the unit vector notation. They told you the acceleration was constant and everything, so clearly there's an x component to the acceleration and a y component, and you were given the amount of time. Yeah, you can do that one on your own. Next one says, a particle moves so that its position as a function of time is... Oh boy, here we go. Not a constant acceleration here. Its position as a function of time is 1 I hat, or just I hat without the 1 in front of it, plus 4t squared j hat plus t k hat. Actually, I think this is a constant acceleration problem. Anyway, it says write expressions for its velocity and acceleration as functions of time, and also what is the shape of the particle's trajectory. Okay, so velocity and acceleration, easy enough. We did a couple of these earlier today. Just take the derivative. Derivative of a constant 1 is going to be 0 in the x direction, plus that's going to be 8t in the y direction, plus derivative of t is just going to be 1 in the z direction, so just k hat is what I will write. And then the acceleration is going to be the derivative of that. Derivative of 8t j hat is just 8 j hat, plus the derivative of, well, 1 k hat, that's 0, so really just don't even need to write anything else. So yeah, it is a constant acceleration actually. I got ahead of myself there. And then part C says what is the shape of the particle's trajectory. So parts A and B were find velocity and acceleration. Part C, what is the shape of the particle's trajectory? What is the shape of the particle's trajectory? Well, it's at a constant horizontal position. It's at a constant position in x. So really, all I have to do is figure out how the y and z components relate to each other. So a way to translate this, r of t equals 1 plus 4t squared plus t, I hat, j hat, and k hat respectively. Another way of saying this is x of t equals 1, y of t equals 4t squared, and z of t equals t. And then from there you can say, well, if z of t equals t, then I can just substitute z in for t, and I can do that over here, and I get y equals 4z squared. This is the equation of a parabola. This is the equation of a parabola. If I were to draw this in 3D, I'll try my best to, but I have a feeling it won't turn out very pretty. So there's x, there's y, there's z. If I were to draw this, let's see, so x equals 1. X is just a constant 1, so we're going to stay in this plane, basically. So in that plane, we've got y equals 4z squared. So it looks like it's going to be a parabola that opens towards the positive y direction like this. And maybe like this as well, although chances are t is supposed to be 0 or greater, so I would probably just use this half of the parabola and that's it. So yeah, it would be in the shape of a parabola. If you ever get asked, what is the shape of an object's trajectory? What is the shape of an object's path? All you have to do is eliminate t and write an equation that relates x to y and maybe to z if there's a z in the question, which there probably won't be because they don't tend to ask you much about the third dimension in physics C mechanics. You can worry about that in electricity and magnetism, but for mechanics they don't tend to ask about the z-axis very much. But yeah, goal for finding the shape of an object's trajectory is just eliminate t, or whatever it is that your x, y, and possibly z depend on, and try and get those 3 coordinates, or 2 if you only have x and y, to relate to each other directly in an equation that only involves them. Eliminate t or theta or whatever it is that's not an x, y, or z. And then see what shape you get based on that. If you get something like x equals some constant times y plus another constant, well, that's the equation of a line. Or I guess more likely y equals a constant times x plus another constant. That's the equation of a line. If you get something like x squared plus y squared equals a constant, that's the equation of a circle. So if you're trying to figure out the shape of something's trajectory, just relate x and y to each other in a single equation and use what you know from algebra. Whatever equation you get, you should recognize from your algebra and pre-calculus courses, oh, this is the equation of a circle, this is the equation of a parabola, this is the equation of a line or an ellipse, or whatever the case may be. You probably won't get an ellipse, but it should be something recognizable. Should be something they can reasonably expect you to recognize. Okay, next question here. Do we want to do this one? It says a particle leaves the origin at time 0 with initial velocity 3.6 I hat and experiences a constant acceleration of negative 1.2 I hat minus 1.4 j hat. And it says, at what time does the particle reach its maximum x coordinate for the first part? The second part is, what is the velocity of the particle at this time? And the third part is, where is the particle at this time? Okay, so reaching, I see, interesting. So we're given basically acceleration. Okay, it's a sort of initial value problem. Let me think. What color do I want to use here? I guess I haven't used... Let me use something brighter. Let's use pink. Yeah, we'll go ahead and do this one. So we're given V0 equals 3.6 I hat. V0 equals 3.6 I hat. 3.6 in the positive x direction. And we are given acceleration is a constant, is equal to negative 1.2 I hat minus 1.4 j hat. So we've got an acceleration that's partly in the negative x direction and partly in the negative y direction. At what time does the particle reach its maximum x coordinate? So this time we actually do have to use the relationship between derivatives and maximum or minimum values, because we do not have x of t, and we don't actually have enough information to define it. So what we need to do, first of all, is we need v of t, and to do that we need to integrate the acceleration. So if I integrate the acceleration, integral of a with respect to time is going to be integral of negative 1.2 plus, or in the I hat direction, plus integral of negative 1.4 with respect to time in the j hat direction. That's going to be equal to negative 1.2t plus, I'll call it Vx 0 for my first constant, and that's in the x direction, plus in the y direction it'll be negative 1.4t plus another constant which I will call Vy0 times j hat. Okay, we were given that at time 0 the velocity is 3.6 I hat plus 0 j hat. So if I plug in 0 for the time here and here, I'm just left with V0 equals, well, 0 plus Vx0 I hat plus negative 1.4 times 0 is 0 plus Vy0 j hat. This is supposed to be equal to just 3.6 I hat, and if you want you can also write plus 0 j hat, which tells me that Vy0 must be 0, and 0 plus Vx0 must be 3.6, so Vx0 must be equal to 3.6. Okay, so V of t then is negative 1.2t plus 3.6, and then that's times I hat plus just negative 1.4t plus nothing in the y direction. So that's V of t. Now they said, where did it go? At what time does the particle reach its maximum x coordinate? When is x a maximum? Well, if we try to integrate this, we can't really find x of t because there's going to be a plus x0 over here and a plus y0 over here for the second component, which we don't have enough information to determine. But that's okay because we have the derivative of x of t. We don't have x of t, but we do have the derivative of x of t, and we mentioned last time that a function will have possible maximum or minimum values wherever its derivative is 0 or undefined. The derivative of x of t is v of t. We have that. In fact, we're just looking for the x component of v of t specifically. So we're looking for when this is 0 or undefined. When is negative 1.2t plus 3.6 equal to 0? Well, it's never going to be undefined because negative 1.2t plus 3.6 has a value for every t. There is no t that you can plug in here that would give you problems, so there's no need to worry about places where it's undefined, but there is one place where it's 0, and that is at t equals 3. That is at t equals 3. Now, does this necessarily mean that it's a maximum? at t equals 3 or a minimum? We don't know yet, but we can do some math to figure it out. It is a maximum if it's increasing before t equals 3 and decreasing after. Is x of t increasing before t equals 3 and decreasing immediately after? Well, if I try plugging in t equals 2.9999, for example, I would have negative 1.2 times 2.999 is going to be something negative that when added to 3.6 gives you 0.00001 at some point, right? So it's going to be positive for values slightly less than t equals 3. What about when t equals slightly more than 3, like 3.001? Negative 1.2 times 3.001 is going to be negative 3.600 something, which doesn't completely cancel out with the 3.6. I'm still going to have something negative left over. So I have positive velocity before and negative velocity after t equals 3. That must mean that at t equals 3 I have a maximum for x of t. So yeah, at t equals 3 seconds is when the maximum occurs. We don't know what that maximum is though, because to figure out what x max is, we would actually have to plug 3 into x of t. We don't know what x of t is because we don't know any initial values for x of t. If we tried to integrate v of t, we would be left with plus a constant here and plus a constant there, and we don't know anything about those constants. So that's as far as we can go. Second question was, what is the velocity of the particle at that time? That would have to be 0. And then third question, where is the particle at this time? Oh, wait a minute, what? Oh, we do have enough information. I ignored the first sentence. It says a particle leaves the origin at t equals 0. So in fact, we do know. Okay, we do know x of t equals 0, and for that matter, y of t also equals 0. Okay, so I guess this is a reminder to read your problems carefully. But I think we can skip that part. All you would have to do is integrate this again. You would get what? Negative 0.6t squared plus 3.6t for the x component, and you would get negative 0.7t squared for the y component, and then plus 0 and plus 0 for your constants of integration, since we know x of t and y of t both start at 0 now. And plug in t equals 3 and you're good to go. Let's have a look at what else we have listed here. Why did I make such a big list? So we've got those, and then I'm just going to comb through these and see which ones we actually really need. Show that the maximum height reached by a projectile is that value. Yeah, you can do that without calculus. I don't even know why I listed that one, probably because it had the word maximum in it. What about this one? Ball thrown from the ground. Yeah, we don't need that one. Okay, next page. An object is dropped from rest. Find the terminal speed, assuming that the drag force is given by force drag equals bv squared. So we already kind of did that problem earlier with drag force being equal to BV. Yeah, all this calculus that we did back here. But with BV squared, this is going to be a setup but do not solve problem, because doing this with BV squared requires an integration technique that you haven't learned and aren't expected to learn for Physics C mechanics. So we've got, I'll just set it up. So it's dropped from rest and some drag force proportional to BV squared is going to build up. It's going to have some acceleration downward due to gravity. I'm going to say down is positive again. That just makes this type of problem easier to set up. And you would just do net force equals MA equals, using down as the positive direction, mg minus bv squared, and then you would do m times acceleration is derivative of velocity with respect to time equals mg minus bv squared, and I suppose you divide by the m, and that is where you would stop. Because yeah, doing this one, I mean, if you try to separate the equations, if I move the dt over to the right hand side and then divide by all of this, then I get 1 over g minus b over m v squared equal, times dv is equal to dt. If I try to integrate both sides of this, this integral requires a technique known as trig substitution, which if you've done Calc BC, you have learned how to do that and you can figure it out. You should get, if I'm not mistaken, some sort of inverse tangent function, which wouldn't be surprising because the inverse tangent function looks like this. It's going to have horizontal asymptotes, and then it'll do something like that. So it has something in common with the exponential function that we got earlier, which is having these horizontal asymptotes that get approached when you approach terminal velocity. Just something to think about. So yeah, if I'm not mistaken, you should be getting some sort of inverse tangent function if you are curious and you want to go ahead and do it to test your Calc BC skills, but not necessary for the AP exam. They will just expect you to stop right here. They will say set up, but do not solve a differential equation that can be used to find the velocity of this object as a function of time, and that's where it would end for you. Okay, so there's that one out of the way. What's next? What's next? How long does it take for an object dropped from rest to reach 1/2 of its terminal speed? Well, fortunately, we already did that earlier. We know... Where did it go? Where's my... Yeah, over here. V of t equals mg over b times 1 minus e to the negative b over mt. So mg over b was the terminal speed. Mg over b was the terminal speed. So to reach 1/2 the terminal speed, I would have to multiply it by 1/2. So 1 minus 1/2 is what it would need to be. So look for e to the negative b over m times t equals 1/2. Set this expression, e to the negative b over mt, equal to 1/2, and that would be the end of it. I guess you would, let's see, actually maybe we should write it down. So it would be, so we would be looking for e to the negative b over m times t equals 1/2. I would natural log both sides. Natural log of e just cancels with the e, and you're left with negative b over m t equals natural log of 1/2, and then multiply by negative m over b, and you're looking at t equals negative m over b times natural log of 1/2. Now, some of you might be worrying, wait a minute, is this going to be a negative time? No, because the natural log of a fraction is going to be a negative, so it's going to cancel with this negative sign. And whatever the mass is and whatever the b is, those are definitely going to be positive. So yeah, you'll end up with some sort of positive value there. I doubt they would actually ask you this, but I guess it would be like a bonus extra part that they could throw in. You know, like part C or part D of some sort of free response question would be doing all this calculus to get your v of t function, and then one more extra point for solving this. It would be like the 5th or 6th part of a multi-part FRQ. Okay, what else? I have listed here 11, 12, and 23. What do those have for us? Show that for a projectile, oh, I remember this one. Show that for a projectile, the second derivative of the square of the speed with respect to time is 2g squared. Okay, so this is all about notation. This would be kind of extreme if they gave you something like this on the AP exam. I highly doubt they would ever ask you something like this. But if you're planning on a career in physics, you might as well learn how to do this. So it says, show that for a projectile, the second derivative, so they wrote d squared of v squared dt squared is equal to 2g squared. The second derivative of the square of the speed. You're not taking the derivative of the speed twice and then squaring it. That's not the same thing. The derivative of the speed squared is not the same as the square of the derivative of the speed. So yeah, be careful about this. Basically treat v squared as being some new variable. Okay, well, what do we know about projectiles? We know that they've got, we'll just do plain old two-dimensional projectiles, of course. So we know that they're going to have some sort of x of t function equals vx times t. This is assuming, of course, constant acceleration in the y direction and constant velocity in the x direction. So x as a function of time is going to be vx times t, plus, I guess, if there's some sort of x initial. And then y as a function of time would be, let's see, it would be delta y equals vy initial times t, so vy0 times t minus 1/2 g t squared and then plus y0 if you have some sort of starting point. Usually I write these as delta x and delta y with the x0 and the y0 subtracted over to the left-hand side, but I don't think it's going to matter here because, yeah, I'll just assume that x0 and y0 are 0. It's not really going to matter. So they want the derivative of the square of the speed, the square of the total two-dimensional speed. Okay, so the speed, Vx, so v of t in general, is going to be Vx in the x direction plus in the y direction we're going to have whatever Vy0 is and then minus gt. And we know this because if you've got a constant acceleration in the y direction, Vy is equal to Vy0 plus acceleration times time, so plus negative g times t. I'm just using the first equation of kinematics here to get this. So I guess I didn't even need to write this down after all. Yeah, I don't think I did. So v squared over here is really just the square of the magnitude of v of t. So v squared as a function of time is really just this squared is equal to Vx squared plus Vy0 minus gt all squared. And then if I take the derivative of this with respect to time twice, what do I get? So if I differentiate it once, if I differentiate it with respect to time, we'll differentiate it with respect to time twice. So if I differentiate it the first time, the first derivative of v squared of t is going to be first derivative of Vx squared. Well, Vx is constant, so its first derivative is going to be 0, plus derivative of this stuff squared. Well, that's going to be a chain rule, so I've got something squared. The derivative of something squared is 2 times that something raised to 2 minus 1 raised to the first power times the derivative of the inside. With respect to time, derivative of Vy0 is 0 because that's a constant. Derivative of negative gt, that's negative g. So times negative g. And if I simplify this a little, so keeping that derivative outside, we've got 0 plus, that's going to be 2, well, hold on, let me see, distribute the negative g and the 2, so negative 2g Vy0, so negative 2 Vy0g, and then negative 2g times negative gt is positive 2g squared t, and some of you are already seeing where this is going. Now take the derivative again, now apply this outer derivative, and we get, well, this stuff is all constant, so its derivative is 0, plus constant times t is just going to be whatever that constant is, and we're done. some people, especially if you know more calculus, would probably assume from seeing this that you have to do some sort of implicit differentiation here. Nope, you don't need to do that. It's not asking about the rate of change of v, it's asking about the rate of change of the square. So you could treat the square as its own variable. If it helps, you could redefine v squared and call it, I don't know, something else. Call it, what's a letter that we could use here? You could call it q, for example. And then instead of v squared of t over here, you could just call it q of t, if that makes you feel any better. Take the second derivative of q. That way you don't see the square in it and it doesn't lead you down the wrong direction. But yeah, pretty simple process once you know what to do. It's just getting over that initial mental hurdle of understanding what they mean by the second derivative of v squared. Okay, what else do I have listed here? And yeah, this is definitely going to need to be a two-parter. We're 3 hours in and not even through half of the course content. Next up is not that one, but 23. What does 23 say? So 23 here says, a particle moves in a plane according to these two equations. So it says a particle moves according to x equals r sine omega t plus omega rt, and y equals r cosine omega t plus r. I would have called them x of t and y of t, so again, if it's not explicitly written as a function of time, but you can tell just from reading it that it's a function of time, you can go ahead and add the parentheses. You can make this x of t and y of t if you want, if that helps you figure out, you know, which variables you're differentiating or integrating with respect to. But if you can just see that mentally without having to write it down, then that works too. So yeah, it says where omega and r are constants, so that's the other hint they give you, that t is the variable here in case it wasn't obvious through common sense. It says this curve, called a cycloid, is the path traced out by a point on the rim of a wheel that rolls without slipping along the x-axis. Part A says sketch the path, so if you've never seen a cycloid before, here's what it would look like. So let's see, at time 0, we would have r times sine of, that's going to be 0, and that's also going to be 0 when I plug in 0 for t. And over here, so that's x is going to be 0, y is going to be r cosine of 0. Cosine of 0 is 1, so that's going to be r times 1 plus r, so that's going to be 2r, actually. So if r is up here, and 2r is up here, so this would be our starting point. It would be at x equals 0, y equals 2r, and then let's pick some other time when omega t is equal to, let's do pi over 2 in radians. Oh, by the way, I forgot to mention this last time. Anytime you do calculus with your trig functions, they need to be in radians, just like it was for simple harmonic motion when we were doing the time functions of simple harmonic motion. You need to be working in radians when doing calculus with trig. Always, always work in radians. Calculus on trig functions isn't going to work out very nicely if you're doing your trig functions in degrees. So yeah, pi over 2, which is equivalent to 90 degrees, sine of pi over 2 is going to be 0, so that's going to be 0 plus omega r, or omega t, that's going to be pi over 2. So r times pi over 2. So whatever that is, r times pi over 2, it's going to be somewhere in x, and then this is going to be cosine of pi over 2. Wait, hold on. Sine of pi over 2 is 1, so r plus pi over 2r. Okay, so it's going to be a little bit further than, because r would be there, so r plus pi over 2r would be somewhere a little bit farther. And then y would be at 0 plus r. So y would be up here. So somewhere around here, I guess, is where it would be. But, well, ultimately the graph is going to end up looking like this. It's going to be like a bunch of semicircles that just keep repeating is what you would get. I made this too small because I'm running out of space, but that's the kind of shape you should get. If you plug this into Desmos and make sure you keep Desmos in radian mode, I think it will trace it out nicely for you. But in the interest of time, I'm just going to skip ahead to the more important part of this question, which says calculate the instantaneous velocity and acceleration when the particle is at its maximum and minimum value of y. Find the instantaneous velocity and acceleration when at maximum and minimum y. Okay, well, maximum and minimum y would occur when the derivative of y is 0 or undefined. So let's figure out dy dt. I mean, we need to figure it out anyway. For both x and y, we need to figure out the derivative. But dy dt is going to be derivative of r cosine omega t plus r. Well, the plus r, that's a constant. Derivative of a constant is 0, so it's really just this. Derivative of cosine is negative sine, so we've got negative r times sine of omega t. And inside of cosine omega t is a second function, the linear function omega times t. So derivative of that needs to be multiplied in as per the chain rule. So derivative of omega times t is omega, so times omega. That should look familiar from what we saw in simple harmonic motion. And yeah, plus nothing. So when is this equal to 0? That's where maximum and minimum values can occur. So if I set this equal to 0, r and omega are constants that are not 0, so the only way for this to be 0 is for sine of omega t to be 0. Sine of omega t equals 0 when omega t is equal to 0, or when omega t is equal to 180 degrees is pi in radians. So those are your options, at t equals 0 or t equals pi over omega. So either at t equals 0 or at t equals pi over omega is when maximum and minimum values of y occur. And to figure out the instantaneous velocity and acceleration when the particle is at its maximum and minimum value of y, I guess we would also have to actually plug these numbers in and see what happens immediately before and immediately after these times. Well, before, I mean, if you're to trust the graph anyway, before you're rising to this point, and after you're falling from this point. So this is a maximum at t equals 0. At t equals pi over omega, that would be when you're down here. Let's see, at t equals pi over omega, this would be cosine of pi, which is -1, negative r plus r. Yep, that's at 0. Yep. So it looks like I drew my graph correctly. And yeah, you're decreasing until you hit it and then increasing after you hit that point. So that is the minimum, in case it wasn't obvious from just looking at the graph. And now that we have verified that this is a maximum and this is a minimum, they said find velocity and acceleration at those two times. So velocity, we've got an x component and a y component. I'll just differentiate them separately. Well, for the y component, we've already done it. It's -r omega sine omega t. That part's already done. We already calculated dy dt. And then for dx dt, or vx, let's see, derivative of r sine omega t is, derivative of sine is cosine of omega t, and then times the derivative of omega t, because chain rule, that's times omega, plus the derivative of omega r times t, that's just going to be omega times r. Derivative of a constant times your variable to the first power is just that constant. Gotta keep hammering that home. It's one of the easiest derivatives to take once you practice it enough times. Now for the acceleration. Take the derivative of r omega cosine of omega t plus omega r. Omega r is a constant, so if I take its derivative, it's going to be 0. Derivative of r omega cosine omega t. So r and omega are constants. Derivative of cosine is negative sine of omega t. And then times the derivative of the inside, times the derivative of omega t, that's another omega. Negative r omega times omega is negative r omega squared. And yeah, plus 0. As for acceleration in y, we've got negative r omega, and then derivative of sine is cosine omega t, multiplied by the derivative of the omega t on the inside gives us another omega, which multiplies nicely into here, making an omega squared. And they said find what again? They said calculate the instantaneous velocity and acceleration when the particle is at its maximum and minimum value of y. So plug in t equals 0 into Vx and Vy and Ax and Ay, and similarly plug in pi over omega. Let's see what we get from this. We might as well, since we've gotten this far already. Which color do I want to use for this? Let's do orange. So at 0, we have r omega times cosine of 0. Cosine of 0 is 1, plus omega times r. So Vx of 0 is going to be just 2r omega. Vy of 0 is going to be, sine of 0 is 0, so yeah, that was easy enough. Okay, what about t equals pi over omega? Vx of pi over omega and Vy of pi over omega. Vx, if I plug in pi over omega here, I just get cosine of pi, which is -1, negative r omega plus r omega, that's 0. And then over here, sine of pi over omega is, if I plug in t equals pi over omega, the omegas cancel, and I get sine of pi, which is 0. Huh, interesting. Okay, and for acceleration, we've got a x of 0 and a y of 0 are what? If I plug in 0 over here, sine of 0 is 0. If I plug in 0 for cosine, I just get cosine of 0 is 1. And then negative r omega squared times 1 is just negative r omega squared. Okay, acceleration in x of time pi over omega, and acceleration in y of time pi over omega will be what and what? So if I plug in pi over omega here, omegas cancel, sine of pi is 0, and yeah, that's just all one big 0. And then over here, if I plug in pi over omega, omegas cancel, cosine of pi is -1. -1 times negative r omega squared is positive r omega squared. And there we go. Did I do everything right? I'm doubting this over here, so let me double check it. Pi over omega simplifies to a pi, and the cosine of pi is -1. Yep, that's a 0. And then, yeah, that all looks right to me so far. So when at the maximum height, you've got velocity in the x direction is at a maximum. That makes sense to me. This is where you would be moving horizontally the most, and then you start tilting downward, so you have less of a horizontal and more of a vertical. That makes sense to me. And your vertical velocity at that time would be 0. That also makes sense. Then over here, your horizontal velocity is momentarily 0, and your vertical velocity is also momentarily 0. when you're over here. Yeah, I suppose that does make sense, because that's, if we're talking about, because this is also the path traced by an object that's rolling without slipping, and we talked about how when an object is rolling without slipping, its point of contact with the surface is at a velocity of 0 for that split second that it's about to lift off and start rolling off. I'm not sure how to word what it is I'm trying to say here. But yeah, it's consistent with what I already know about objects rolling without slipping. I don't know why, but it just kind of feels wrong. Even though I know it's consistent with other stuff we know in physics. That's the thing about physics, a lot of unintuitive results. Sometimes the intuitive result is correct, and sometimes the intuitive result is not so correct. So when your math and your intuition clash, you can never tell at a glance which of the two is right. Okay, and then in terms of acceleration, when we are at the top over here, you have no acceleration in the x direction. Yeah, that makes sense to me because you're kind of rolling down and you have a negative acceleration in y. Yeah, that makes sense to me. And then when you're over here, acceleration in x is still 0, while acceleration in y is positive. Yeah, that makes sense to me because if you look at it, the tangent to these curves would have to be in the vertical direction, would have to be in the y direction. Actually, I'm not entirely sure I believe this. Well, I'll look over it some more, and if I have any more insights, I will probably post something in a pinned comment later. Because I feel like something might be wrong here, but maybe I'm just doubting myself too much. Anyway, let's see what else we have lined up here for today. So that was some kinematics stuff for the most part, mixing in a little bit of force. Let's do a little bit more with force over here and see if we can get into maybe energy. So with force I've got, let's see, it was page 107. What do we have for force? 48, 49, and then problem section 20. Let's see what those were all about. Okay, yeah, so the biggest thing that's purely in the force chapter is forces that depend on time. We saw a force that depends on speed in the drag force. The only other things where you would have to do calculus with force would be forces that vary with time and forces that vary with position. And as for forces that vary with position, we will see more of that in the work and energy section, which might be the last thing we get to today before I have to call it quits. Because my goodness, this is definitely taking longer than I would have expected. just goes to show that I'm not that good at gauging how long it takes to teach these things. Had the parent of a student the other day looking at my playlist and questioning why every video is like 3 hours long. Oh, speaking of, actually, I forgot to bring this up. So apparently, I had the playlists for this course unlisted for some reason. I don't know why. I think when I originally created them, they were unlisted because there was no point in showing them when they only had like one video in them, and I just forgot to go back and make them public, but they should be public now. So if you want it all organized in one nice playlist, it should be there in a playlist on my channel. So if you just click on, my icon under this video and go to the playlists tab, you should find it there. But also, I think I have it just on the main page as like a horizontal thing. I think YouTube calls it a shelf or something like that. So whether it's directly from the main page or from the videos or playlists tab, you can find it all in one playlist, or probably YouTube will just recommend the playlist in the top right corner after a while, because I know YouTube has a tendency to recommend the playlist for videos that are part of a list sometimes, but not always. Anyway, which problem was I looking for again? Oh, right. So here we've got a force that varies with time. Pretty simple to deal with, actually. So it says the position of a particle of mass 2.17 kilograms traveling in a straight line is given by x equals 0.179, and that's meters per second to the fourth, times t to the fourth, minus 2.08 t squared plus 17.1. And this is all going to work out to be in meters. The 0.179 is in meters per second to the fourth, which becomes meters when you multiply it by t to the fourth, since t is going to be in seconds. This is 2.08 in meters per second squared, which again turns into meters when you multiply by seconds squared, and 17.1 is straight up in meters. The mass was given as 2.17 kilograms. And it says, find the velocity, the acceleration, and the force on the particle at time 7.18 seconds. Okay, I'm just going to focus on that last part. What is force at time 7.18 seconds? Really easy to do. It's not that complicated. This is really just a problem for the sake of having a calculus-based problem. So you would just do, that net force is equal to mass times acceleration is equal to, in this case, just whatever our mystery force is just equal to f of t plus nothing and minus nothing, because they didn't mention any other forces that would be acting on this particle. So just divide by mass, and you've got, or actually don't even divide, just keep it like this. So f of t is equal to m times a of t, and to get a of t, just take the derivative of x of t twice. So we've got equals mass times second derivative with respect to time of x of t equals, if I take the derivative of this thing once, I multiply by 4 and get t cubed. If I multiply it, or if I differentiate again, I multiply by that 3 and then get t squared. So multiply by 4 and 3, multiply by 12, and we get m times, that's going to become 12 times 0.179 t squared minus 2.08 if I differentiate this twice. First time I multiply by 2 and decrease the exponent to 1. Second time I multiply by 1 and decrease the exponent to 0, which just removes the t. So it's just 2 times 2.08. And then the derivative of 17.1 twice. If I take its derivative the first time, I get 0. And if I take the derivative again, derivative of 0 is still 0, so plus nothing. And plug in t equals 7.18, plug in m equals 2.17, and you're done. That's it. Easy question. Plugging in the numbers is a step that I will skip because you all know how to do that. I hope you guys can appreciate me varying the notation that I've been using for my derivatives here and there. Last time we had to do a double derivative, I just wrote this as d over dt twice in a row, but d squared over dt squared also works. I guess I haven't really been using the prime symbol for differentiation much. Let's see if we can use that on this next one, which says, a particle of mass m is subjected to a net force F of t given by F of t equals F0, F of t, vector F of t equals F0 times 1 minus little t over big T I hat, and that's it. There are no y or z components. Okay, and it says that is f of t equals f0 at time 0 and decreases linearly to 0 in time big T. Okay, the particle passes the origin x equals 0 with velocity v0 I hat. So when x equals 0, vx equals v0 I hat. Okay, so far everything seems to be in the x direction. Show that at time t equals big T, that f of t vanishes, or show at the instant t equals big T that f of t vanishes, the speed v and distance x traveled are given by two equations that they want us to derive, where, okay, so it says show that at t equals big T, v of big T equals v0 plus a0 times big T over 2, and x of big T equals v0 big T plus a0 big T squared over 3. And they're also defining a0 equals f0 over m. So that is the task. Okay, which color do I want to switch to? Let's do pink for this. I think I'm going to need to get up and stretch for a minute after this one. So we were given some initial values over there. What else did they tell us? And also f of t is equal to f0 at time 0. Yeah, that makes sense just given the formula they gave us. Yeah, I think we have all the information we need written down, so let's see what we can do. So we've got the force function, which means if we simply divide by mass, then we would have the acceleration. They told us this was the net force, so dividing by the mass gives us acceleration as a function of time equals f0 over m. They called this a0 times 1 minus t over big T, and that's in the x direction. I suppose I could also call this a sub x and then not have to write the I hat, which also works. And then to get velocity, you would just take the integral of acceleration. So if I integrate this, then I get v of t equals, if I integrate this with respect to time, integral of 1 minus t over big T with respect to time, and then of course times the I hat. The integral of 1 is equal to t minus 1 over big T, that's a constant, and then the integral of t becomes t to the second power divided by 2, so that's going to be 1/2 t squared, so 1/2 and then t squared, and then the big T is a constant that stays in the denominator, and then plus the constant of integration, and all that times I hat. And I think I'm going to continue this on another page. So we need to figure out what this constant is before we integrate again. I mean, we could integrate again and keep this constant in there, but that is probably going to be a bigger mess. So we might as well figure this out now. They told us when x equals 0, vx equals v0. Oh, well, we don't have x of t yet, so yeah, I guess technically we can't do anything with this plus c yet. Okay. We will continue then. I'll use this last bit of space to write down my x of t, and then we'll move on to another page. So x of t is going to be the integral of v of t with respect to time, is going to equal the integral of t minus 1/2 t squared over big T plus c dt. Let's see. And then if I integrate t, that's going to be 1/2 t squared minus 1/2, let's see, this t squared becomes t cubed divided by 3. So dividing by 3, and we already have a 1/2, so that's a 1/6. and then t cubed over big T, and then plus the integral of a constant is the constant times the variable, so ct. So that's going to be our x of t for now until we plug in some initial values and see what we can figure out. Oh, plus another constant. I guess we'll call this x0 instead of calling them c1 and c2. I'll just call the new constant x0. Okay, moving on to another page. Or do I have... Oh, I've actually got the backside of that page. Okay, so let's see, t minus 1/2 t squared over big T. So v of t equals t minus 1/2 t squared over big T plus c in the x direction. Come to think of it, yeah, I guess I forgot the I hat over here. I mean, is it really necessary when we've explicitly written this as x of t? Probably not. And 1/2 t squared minus 1/6 t cubed over big T. Plus ct plus x0 I hat, and I feel like I'm forgetting one other thing. What am I forgetting? Oh, I forgot the a0 out here. Yeah, multiply. Oh, that's quite the big blunder. Big blunder. So multiply by a0 over here, and then that times a0, which would mean that this stuff would also be multiplied by an a0. Yeah. Okay, well, at least it's fixed with a simple multiplication. Okay, there we go. Now, we were told when x equals 0, vx equals v0. So when does x equal 0? It says the particle passes the origin x equals 0 with velocity v0 . So when x is equal to 0, so if I... Wait, is this at time? Hold on, let me reread the problem again. A particle of mass m is subjected to a net force F of t given by F of t equals F0 times 1 minus t over big T I hat. That is, F of t equals F0 at time 0 and decreases linearly to 0 in time big T. The particle passes the origin, x equals 0, with velocity v0. Show that at the instant t equals big T that f of t vanishes, the speed v and distance x traveled are given by v of t equals v0 plus a0 t of t over 2, big T over 2 rather, and x of t equals v0 big T plus a0 big T squared over 3, where a0 equals f0 m over m rather is the initial acceleration. Do they want us to assume that at time 0 x equals 0? It looks like it. Yeah, it looks like at time 0 they want us to just assume that x equals 0, so okay, we can write that off. If you plug in 0 for the time, then that's when x equals 0. Which would mean that this c, if at time 0 is when x equals 0, then v of 0 should be what they called v0 I hat over here. Okay, so yeah, just they could have worded that more explicitly. Like, I see what their intent was, but they could have worked on the wording of that problem. Okay, so C is equal to V0. And X0 is equal to 0. That is what they intended, but they just did a bad job with signaling that intent. So now that we have that, we can rewrite V of t is equal to A0 times t minus 1/2 t squared over big T plus V0. And x of t equals A0 times 1/2 t squared minus 1/6 t cubed over big T plus V0 t plus nothing. And those are both in the positive x direction. Okay, so show at the time t equals big T that we get those two results. So just plug in big T and let's see what we get. If I plug in big T for little t, then V of big T equals A0 times big T minus 1/2 big T squared over big T plus V0 I hat, and x of big T equals A0 times 1/2 big T squared minus 1/6 big T cubed over big T plus V0 big T. We have t squared over t simplifies to just a t, just one big T, and then t, or big T minus 1/2 big T would just be 1/2 big T, so we've got A0 times 1/2 big T plus V0. And then over here, we've got A0 times, let's see, 1/6 of T cubed, big T cubed over big T is big T squared, and then 1/2 big T squared minus 1/6 big T squared. A half minus a sixth is 1/3, so that's 1/3 big T squared plus V0 big T times I hat. Does that match what we have over here? No, it doesn't. What did I do wrong? I know what I did wrong. the A0 distributes to the stuff inside the integral. The plus c needs to be left out of it. So I put my parentheses in the wrong place. This parenthesis. Well, actually, no. We still need that parenthesis to keep the I hat out. It's just we need another layer of parentheses here. The A0 distributes over the t minus 1/2 t squared over big T, and then put even bigger parentheses around there. I guess I'll need to move that equal sign out of there. Yeah, something like that. And then same thing over here. The A0 only distributes to these two terms. It doesn't distribute to the CT term. So put that there, and then I guess I'll use a square bracket for this, and then a square bracket surrounding that. And then I guess I'll move my equal sign out here, even though it's really cramped and it doesn't really look right, but okay, I see what I did wrong. So the A0 only distributes to here. Yeah, something like that. Close parentheses there, and then, yeah, that looks better. So then we would do, let's see, close parentheses there. That's going to be a bracket. Okay, did I do all that right? I'm still missing close parentheses there. Oh, goodness. Well, at least I caught it. That's the important thing. And then close parentheses there. Okay, that should do it. So now I've got A0 times 1/2 big T plus V0 and A0 times 1/3 big T squared plus V0T. Is that right? A0 times 1/2 big T plus V0 and A0 times 1/3 of big T squared plus V0T. Okay, there it is. So just issues with placing parentheses. And I think that was the last one out of that set. So let's take a look at work and energy, and then we will have to wrap up with that, it looks like. So work and energy. And then we'll have to do a follow-up to this in a separate stream. Might have time to do it tomorrow, but we'll see. If not tomorrow, then I think it's either Wednesday or Thursday that I might have the next good opportunity. Okay, let's see over here what we've got. Here we go. Okay, so before I dig into a problem, let's just talk about what changes for work and energy now that calculus is involved. Two things, really. Just the way we calculate work if it's done by a variable force, and also the way that potential energy is defined. So Without calculus, what we assume when calculating work is that the force is constant, and we take that constant force, we multiply it by the displacement, and of course times the cosine of the angle between their directions, and we get whatever the work is. We get some constant, some scalar value. So in the case where the force varies with position, which we already actually dealt with before in the form of springs, right? The spring, the force that it exerts changes as it stretches and compresses. In cases like that, what we need to do is, instead of calculating the work in one fell swoop over one large displacement, what we do instead is we calculate the work done over a very, very tiny displacement. Instead of a big displacement delta x, we take the force, which is going to be a function of x, and we multiply it by a very, very tiny displacement. Instead of delta x, we multiply it by a tiny displacement dx. Over the course of a very tiny displacement, force as a function of x is going to be kind of constant. The force is going to be fairly constant if we don't move too far in x. So we would take f of x, which is approximately constant over that very short dx, and calculate a very tiny amount of work called dw. And then we would move on. We would move on to the next x value, which for which f of x is approximately constant. Multiply it by a very, very tiny change in x. Add that to the stack and just rinse and repeat. Add this repeatedly. That would be our Riemann sum. We would just be taking the sum of, if I had a force versus position function that looked maybe something like this, for example, we would just take really, really tiny displacements. So here's a very tiny displacement, whatever this displacement is, multiply it by the force that's approximately constant here, you get that tiny amount of work dw. You move on to the next one, treating it as being approximately constant. You add that to the total, and you keep on going and going and going. You take infinitely many of these rectangles. If you saw my video on Riemann sums, then you saw, at least for the case of the quadratic function, f of x equals x squared, I believe was the example I did in that video, you at least saw there how the power rule for integration came about, how it turned out to be 1/3 x cubed when the function was x squared. And I could have probably taken a lot more time to prove it more generally using like the binomial theorem, but I think there's already a good like Khan Academy video going over that. So if you really want hardcore proof of the power rule for integration, you can go and do that. My point here is just this style of thinking, taking when you have something that is a mathematical nuisance because it's constantly changing, the way to deal with that is to take whatever variable is causing it to change and take very, very small changes in that variable, which allow you to then treat the function as being constant for that very short interval, and then start stacking those tiny bits of the total that you're trying to calculate and add them up. That's what an integral does for you. An integral, like I said last time, is really just a sum. You're taking basically an infinite number of these tiny bits of, in this case, work, and adding them all up. So yeah, work, if I integrate both sides of this, then I get work is equal to integral of f dx, or dy, or dr if we want to be more general about it. And of course, you multiply by the cosine of the angle if there's an angle between the direction of dr and your force. So work, actually the way it'll be written in multivariable calculus is like this, f dot dr. And then over here, multiply that by cosine of theta. This cosine of theta over here, this version of the integral, only really works if the angle between the force and the tiny displacement differential is constant. If it's not constant, then, well, I would hope that you don't have to deal with that. I can't really think of a scenario where you would. There's only two situations that I can see. Either cosine of theta is equal to 1 or cosine of theta is equal to -1. Those are really the only two possibilities that I would expect you to encounter on the AP exam. I wouldn't expect a varying theta, though. That I definitely wouldn't think is fair. But yeah, however you want to write it, work is the integral of force is usually going to be a function of position, and then multiplied by a tiny change in position, dr, dx, dy, whatever is appropriate for the problem at hand. Okay, so that's work, and we know by the work energy theorem that work is equal to the change in kinetic energy. So we can also say change in kinetic energy equals the integral of f dr. But if mechanical energy is conserved, that is, for a conservative force, then we can say change in mechanical energy equals 0, but change in mechanical energy also equals change in kinetic energy plus change in potential energy. So if I solve for change in potential energy, then I can say change in potential energy equals, subtract change in kinetic energy over to the 0 side, equals negative change in kinetic energy equals negative integral of force times dr times the cosine theta when appropriate, of course. Just because I'm neglecting the cosine theta doesn't mean it's not there. It's just that it's usually equal to 1. So be sure to remember that. So yeah, for a conservative force, we can actually calculate the change in potential energy due to it just by taking the negative integral of that force. So I'm going to call it F conservative, F con times dr. Okay, this allows us to then derive a formula that we've been using but never actually went out of our way to prove, which is the formula for gravitational potential energy in the universal perspective using Newton's law of universal gravitation. So for Newton's law of universal gravitation, we can do change in potential energy equals negative. The conservative force in that case would be the force of gravity, G, M, over r squared integrated with respect to r, and then times the cosine theta. Here the cosine is actually going to be relevant, so let's define our directions and make sure we understand which way we are integrating. So we're talking about, let's say, the planet Earth and something that moves between two different positions relative to the Earth, two different distances from the Earth. Let's call this R1 and let's call this R2. Okay, if I want the change in potential energy for an object that is going to move from R1 to R2 under the force of gravity, then we have negative integral from R1 to R2 of gmm over r squared dr times cosine of theta. So what is the direction of the force of gravity? The direction of the force of gravity is going to be, well, towards the planet. That's going to be the direction of the force of gravity. What about the direction of r? The direction of r, it increases as you go away from the planet. So r is defined from the center of the planet and outward. That is the direction of r. That is the direction of our position vectors. So that means that they're going to be facing opposite from one another. So cosine of theta, that's cosine of 180 degrees, that's a -1. So I guess these negatives cancel out, but that's okay. We're still going to end up with a negative in the end, because change in potential energy, I'm going to say potential energy at position 2 minus potential energy at position 1 is equal to, let's see, g and the m's, those are constants. I can pull them outside of the integral. And I'm left with 1 over r squared. I'm going to rewrite that as r to the -2. Okay, r to the -2, power rule says increase the exponent by 1 and divide by the new exponent. So -2 plus 1 becomes -1 and divide by -1. So we get r to the -1 divided by -1. That gives me negative gmm r to the -1. That's 1 over r. And then we evaluate that from R1 to R2. From R1 to R2. Okay, let's continue this up here. I have a tendency to do things right to left for some reason. So potential energy 2 minus potential energy 1 equals, let's see, negative gmm times, we do 1 over R2 minus 1 over R1. And if I distribute the negative gmm, then I've got potential energy 2 minus potential energy 1 is equal to negative gmm over R2 plus, well, let's do minus negative gmm over R1. So this tells us then that the formula for potential energy in general in the universal perspective is just negative g m m over r. But we can still apply potential energy change equals negative integral of conservative force with respect to r, even if it's not this type of potential energy. Anything they could throw at you, they could give you something, they could like give you a graph and say, oh, here's a force, and take our word for it, it's a conservative force, and determine what the potential energy function for such a force would be. They could give you something like that. They could just give you something random. And I think I actually had a few of those picked out among the problems that I listed in my notes, so we might see some of that today. But at the very least, we've now derived this formula. In case you were uncomfortable using it all this time, now we actually have a sense for where it came from. Let me think. What else did I want to say here before moving on to problems? Oh, right. Of course, you could also find the force if you know the potential energy function. So if the potential energy function is equal to the negative integral of force with respect to position, then you can also do the reverse. You can define a derivative. So you can say that a conservative force is equal to the negative derivative of potential energy with respect to position. Because if you just rearrange this, this is really just a separable differential equation here. Just move the dr over and multiply both sides by -1. And now integrate both sides, and what do you get? Integral of dPe is just the potential energy change, equals integral of -f dr. So yeah, you can use it in either direction. You might be given the potential energy function instead and asked to find the force. A lot of times what they like to do is they'll give you a graph, and instead of PE, they will just use U on the AP exam for potential energy. And they'll say, here's U of X, and here's X, and they'll tell you that it's a conservative force, and you know, they'll have some sort of graph. Maybe it'll do something like this or something like this, and maybe have an asymptote or something. And they'll tell you what is the force at, I don't know, at x equals, say, whatever this value is. And then you would go and you would calculate the slope over here. And then what a lot of students will mess up is they'll forget the negative sign in this relationship. And they'll get the direction of the force wrong and miss some points because of that. But otherwise, pretty simple type of question they could ask you. So yeah, if you have a potential energy function, don't worry about where that potential energy function came from or if it even makes sense. Just remember that you can get the force by taking the negative derivative of the potential energy. Okay, now we can look at a problem or two. And by a problem or two, I mean like 3 to 7, most likely. How many do I have listed here? I've got 1, 2, 3, 4, 5, 6, it looks like. Oh, wait. No, that's just one section. 7, 8, 9, 10, 11, 12. Okay, I've got 12 different problems listed. Let's see how many of them are actually good. So this first one is a multiple choice. It's work done by a variable force. It says, the force exerted by a special compression device is given by, what color do I want to use for this? Let's do green. So they have the force exerted by a special compression device is given by F sub x of x is equal to kx times x minus L. And this is for x falling between 0 and L. So x is 0 at minimum, L at maximum, and k is a constant. And it says, first question, the force required to compress the device a distance d is a maximum when, and your options are Fx of d is a maximum when choice A, d is 0, choice B, d is L over 4, choice C, d equals L over the square root of 2, choice D, d equals L over 2. Is that still visible on the screen? Yes, it is. And choice E, d equals L. When is this force a maximum? Well, you could use calculus on this, but do you need to? We know that to find the maximum of a function, we can just take its derivative and figure out where that derivative is 0 or undefined, and then once we have a number, test a number slightly less and a number slightly more, and confirm whether it's a maximum or a minimum or just nothing. But we don't actually need calculus here. We don't actually need calculus here because this is just a quadratic function. This is just a quadratic function. If you multiply the kx into here, you get the force as a function of x is equal to kx squared minus kxl. That is a quadratic function. And then to find where it is a maximum or a minimum, you would just do negative b over 2a would be the axis of symmetry position for this quadratic function. So you would do negative KL over 2k. The negatives cancel out, the k's cancel out, and we're left with L over 2. We are left with L over 2 which would be choice D, but also we need to check whether it's a maximum or a minimum. I guess in this case it's actually a minimum because this, well, I would assume K is a positive constant here. Hold on. The force exerted by a special compression device is given by f of x equals kx times x minus L, where x is between 0 and L. So x minus L is going to be some negative over here. So the direction of the force will be opposite to the direction of its displacement. Yeah, that does resemble some sort of funky spring, which is what I would expect. Yeah, but this would have to be a minimum, not a maximum. That would have to be a minimum. So then the maximum then, okay, the maximum then would not be at L over 2. This would have to be a minimum because this is a graph that's going to be concave up if K is positive. So then the other thing I need to test is places where the derivative is undefined, and that includes the endpoints. So at x equals 0 and at x equals L, I need to test those as well. So we can plug in L over 2, and we can plug in x equals 0, and we can plug in x equals L. If I plug in x equals 0, I get 0 minus 0, no force, okay. If I plug in x equals L over 2, then I get k L squared over 4. I get k L squared over 4 minus k times L over 2 times L. So that's k L squared over 4 minus k L squared over 2. A fourth minus a half, that's going to be negative k L squared over 4. That's going to be negative k L squared over 4. The negative is just an indication of direction. Oh, then it could still be the maximum then, as long as its magnitude is greater than what we get for L. When x equals L, oh, well, x minus L is 0 and then 0. Okay. Okay, so it does in fact occur at L over 2. It does in fact occur at D equals L over 2. Okay. And then part B says the work required to compress the device a distance D is a maximum when D is equal to 0, L over 4, L over square root 2, L over 2, or L. So it's the same 5 answer choices as before, but this time it's asking for the work required to compress the device some distance D. So this time it's asking about when the work is a maximum. When is W a maximum? Well, work is the integral of my variable force with respect to position. And when is work a maximum? Well, when its derivative is 0 or undefined. And if work is the integral of force with respect to position, then the derivative of work is just the force function that I already have. So work is a maximum or is likely to be a maximum, when force is undefined or 0. Force is 0 for x equals 0, and for x equals L, and that's it. So it's either 0 or L. We need to pick between A and E. We need to pick between A and E. Well, let's see. So, is the work negative just after x equals 0? If I plug in an x value greater than 0, whatever it may be, some positive x value, which is still less than L, then I get something positive here times something less than L minus L. That's something negative. So I've got a positive times a negative. I'm getting a negative force there. Negative force by the device, but it's asking about the work required to compress the device. So it's asking about the work done by the person or machine that's pushing the device, which would be positive. So the device would apply a force in a negative direction, but the person pushing it would be applying a force in the positive direction. So x equals 0, or rather d equals 0 might be the right one here. Let's see, and then the other possible candidate is x equals L. If I stop just shy of L, well, the whole time the force is going to be negative. The whole time the force exerted by the compression device is going to be negative. So that means the whole time whoever is pushing the device is doing positive work. So if they're doing positive work up until x equals L, yeah, it would have to be E. Yeah, so this required more physics thinking than calculus thinking. You have to really kind of picture the situation in your head, and it's not exactly a spring, but if we treat it like it is a spring, I would, for intuition's sake, draw it like this, with the device being on the right-hand side. So somebody's going to apply a force on this thing and compress it by a distance d, and it's going to apply a force in the negative direction, and it's going to keep applying force in the negative direction up until you compress it a distance L. So over the course of all of that compression, some positive work is being done by whatever that external force is. Yeah, that work would be maximized at d equals L, because at no point in between its uncompressed state and its fully compressed state, at no point in between those two positions will the total work ever decrease. It only ever increases from the moment you start pushing it up until it's pushed all the way back. The direction of the compression force doesn't change on the interval from 0 to L. Okay, so as you can see, knowing your physics concepts is still very much an important part of these problems. Probably way more important than the calculus itself. Now then, what else do we have? I listed 25 and 31. Let's see if they were any good, or if past me was just out of his mind. Did I really mark this as a... Okay, it says by integrating along the arc, show that the work done by gravity in sample problem 11.5 is equal to negative mgh. Where is that sample problem? Because I usually skip problems like this. Problems that refer to figures and equations that were somewhere within the chapter I usually tend to skip. What do we have here? A small object of mass m suspended from a string of length L. The object is pulled sideways by a force F that is always horizontal until the string finally makes an angle phi m with the vertical. The displacement is accomplished at a small constant speed. Find the work done by all the forces that act on the object. Okay, and the question for us is by integrating along the arc, show that the work done by gravity in the sample problem is equal to negative mgh. By integrating along the arc. So they want us to do what? They want us to do, we'd have a variable angle. Yeah, I'm skipping this one. I don't think they would ask you anything like that. But if you are curious, basically, it's just a pendulum sort of thing that they pull from its downward hanging position up by some height h, such that it makes some specific angle. Okay, what about 31? It says a force acts on a 2.8 kilogram particle in such a way that the position of the particle as a function of time is given by x equals 3t minus 4t squared plus t cubed. Find the work done by the force during the first 4 seconds, and then at what instantaneous rate is the force doing work on the particle at the instant t equals 3 seconds. Should be a pretty decent problem for us. So it was, the mass of the particle is 2.8 kilograms, might be useless information or might be relevant. We'll see as we go. We are given x equals 3t minus 4t squared, 3t minus 4t squared plus t cubed. And it says find the work done by the force during the first 4 seconds. Find work in first 4 seconds, in first 4 seconds. And then it says, well, we'll worry about that later. Find the work in the first 4 seconds. Well, in 4 seconds, its position changes by a certain amount but we need to figure out the force. Considering the way that the position is changing, it looks like we've got a variable force because we've got a variable acceleration. If I take the derivative of this twice, we've got velocity in the x direction is equal to the derivative of x dx dt, or I guess we'll call it x prime of t, since we haven't really been using the prime notation for derivatives today. Might as well have a look at a few examples using that notation. So that's going to be 3 minus 4t squared is going to become 8t to the first power, and then plus 3t squared. Okay, the acceleration in the x direction, which is vx prime of t, or x double prime of t, is just the derivative of that derivative. Derivative of 3 is 0. Derivative of negative 8t is negative 8. And the derivative of 3t squared is 6t. And then the force in the x direction would be just ma equals 2.8 times negative 8 plus 6t Okay, and it says find, where did it go? Find the work done by the force during the first 4 seconds. So we have force as a function of time. We don't have force as a function of position. So we can't find the work doing the integral of f dr, or in this case f dx. We cannot do that. Integral of f dx to find work, not going to help us. However, we do have something else that we can use. Something that gets forgotten a lot by physics students, which is another formula for work. What else is work equal to? We used it earlier today. Work is equal to the change in kinetic energy, the work kinetic energy theorem. Work is equal to 1/2 mv final squared minus 1/2 mv initial squared. V we do have. V final and V initial we do have. Just plug in, they wanted the work done in the first 4 seconds. That means we would use V of 4 and V of 0. So our V final in this case would be 3 minus 8 times 4 plus 3 times 4 squared, while V initial would be 3 minus 8 times 0 plus 3 times 0 squared. And that's your V initial and V final. Plug them in over here. You have the mass as 2.8, and you can calculate the work from there. I will skip plugging in the numbers. Let's move on to the second part, which said, at what instantaneous rate is the force doing work on the particle at the instant t equals 3 seconds? The rate that the force is doing work on the particle. The rate of work being done. There's a concept we haven't played around with in a while. The rate at which work is being done. What was the name of that again? That's power. That is power. Power we normally calculate as work over time, but we can also calculate it as dw dt. Also, work over time does translate to force times velocity, so another thing you could end up doing, since work is force times velocity, another thing you could end up doing with power is you could end up calculating power as an integral, where you could do, if force is a function of velocity, it would be the integral of force as a function of velocity times a small change in velocity. I suppose maybe you could do something here with like air resistance, since that would be an example of force as a function of velocity. Maybe. Otherwise, the alternative would be an integral of velocity as a function of force, which is less likely, but you could see it. Honestly, you're not very likely to do an integral for power either way, but you could also get a scenario where it's VDF instead. But yeah, I highly doubt that you would have to do either of these. Don't count on it. Like, out of all the things you should be studying, this is not even at the bottom of the list. This is so far down the list that it's not even on the list. At least if you ask me. Anyway, so we were looking for, it was asking us to get the instantaneous rate that the force is doing work on the particle at the instant t equals 3 seconds. Well, we could figure out exactly what the force is at 3 seconds and exactly what the velocity is at 3 seconds and just multiply those and be done. Power at 3 seconds equals force at 3 seconds times velocity at 3 seconds. Yeah, that's what I would do. Plug in 3 over here, plug in 3 over here, multiply those two results and you're done. We didn't have to do calculus for that one. We just had to reuse the calculus we did in the first part. All right. Next up, we have, in the problem section, I highlighted 10, 11, and 13, it looks like. Let's give them a read and see. Number 10, oh look, more power stuff. The power output from a motor on a trolley is a function of velocity and is given by P of V equals AV times B minus V squared, where A and B are constants, and P equals 0 for V squared greater than B. Oh my goodness, let's write this all down before we continue reading it. So, it's telling me power curly P as a function of velocity is equal to AV times B minus V squared, where A and B are constants, and they also say P, I keep writing a regular P because I'm reading it off of the book as a regular P, but I like to write it as a curly P because I don't want to confuse it with the capital P that we use for pressure, or the lowercase p that we use for momentum. Anyway, so it said P equals 0, so P equals 0 for B greater than v squared, or no, other way around, for b less than v squared. So in other words, b minus v squared needs to be a positive value. If b is any less than v squared, then the power just drops to 0 and stays there. Okay, so it said, at what speed is the maximum power output from the motor? So P max at what V? Their second question was, at what speed is maximum force exerted by the motor? So F max at what V? And their third question says, at V equals 0, the power output is 0. Does this mean that the motor will be unable to move the trolley if it's originally at rest? Explain. Okay, we'll look at that after doing the other two questions. So, let's see. When is power a maximum? When is power a maximum? So, to find the maximum of a function, we could just take the derivative and set it equal to 0. Do we need to do that here, though, or can we just do it using algebra-based techniques? Because this looks like a quadratic. So, yeah, I'm just going to do regular algebra-based techniques here. Multiply the... Oh, wait. No. Because, yeah, that's going to become negative AV cubed. Okay. Calculus is needed, but we still need to distribute the AV anyway, because otherwise you would need to do the product rule, which I did not have you guys learn in the previous episode. It's not something that's expected of you on the AP exam. So I'm going to rewrite power as, if I distribute the AV, I get ABV minus AV cubed. And then if I take the derivative of power with respect to velocity, I get derivative of ABV is just AB minus derivative of AV cubed is going to be 3AV squared. And then I want to set this to 0, so AB minus 3AV squared equals 0 when AB is equal to 3AV squared. Cancel the A's, and it looks like V squared equals B over 3, which means V equals square root of B over 3 would be our candidate for a maximum. Let's see if that works. If I plug in square root of B over 3, well, let's see. So if I plug in square root of B over 3 for V, then I get AB root B over 3 over here, and I get 1/3, wait a minute, and then I get AB over 3 times root B over 3. That's not right. Oh, wait, I plugged it into the wrong place. You plug it into the derivative function. I was plugging it in up here. Wrong. You plug it in here, and you see if you see if it's a switch from positive to negative. So if I plug in something less than b over 3. Let's say, for example, b over 6, square root of b over 6. ab minus 3a times square root of b over 6 when squared is just b over 6, so that's 3ab over 6 is 1/2 ab minus 1/2 ab. That would be positive. So it's positive before the square root of b over 3. What about if I pick something a little bit more than square root of b over 3? What if I do square root of b over 2? That would be 3a times b over 2. So that's 3/2 ab. ab minus 3/2 ab is negative 1/2 ab, which is negative. So the derivative is positive, indicating increasing. Then it hits 0 at square root of b over 3, and then it goes to negative. So increasing, peak, decreasing. That does mean that we do indeed have a maximum at v equals square root of b over 3. So v equals square root of b over 3 is where we get a maximum power output. And to figure out what that maximum is, you plug this in to the original power function. So to test whether it's a maximum or a minimum, you plug it into the derivative, but to actually figure out what that maximum or minimum is, you plug it into the original. Now, what is the v at which the force is a maximum? F is a maximum at what v? Well, F is equal to P over V. Force is equal to power over V. So if my power is AV times B minus V squared, then F of V is AV times B minus V squared over V. Cancel a V, and you've got F of V equals, I'll distribute the A, AB minus AV squared. To figure out where the force is a maximum, I'll take its derivative. So F prime of V equals derivative of a constant is 0. Derivative of negative AV squared, that's negative 2AV. And then if I set that equal to 0, then that would imply, since A is a constant, that V has to be 0. So if I test at V equals a little less than 0 and a little more than 0, F prime of V equals 0 when V equals 0. If I plug in something a little less than 0, so negative, then I get negative 2a times a negative, that's a positive, so that's an increase before v equals 0. And after v equals 0, so if I plug in something like v equals 0.001, then I get something negative. Negative 2a times whatever is negative. So positive derivative, then 0, then negative. Increasing, then 0, then decreasing. That is indeed a maximum. So yeah, it's going to be when v equals 0. As for what is that maximum, plug in 0 for v into the original force function and you get the maximum force is AB. Come to think of it, I guess we could have done that without calculus. I mean, just looking at this, if you're only ever subtracting from it, then it makes sense for you to subtract nothing here to get the maximum value of this. Yeah, we totally could have done this without calculus, but I rushed it without thinking. Anyway, now then, they had this question of, where did it go? There it is. So it said, at V equals 0, the power output is 0. If you plug in V equals 0, yeah, A times 0 times whatever this is, definitely 0. Does this mean that the motor will be unable to move the trolley if it is originally at rest? Explain. Does the power being 0 mean that the trolley will be unable to move if it starts from rest? The power may be 0, but what about the force? The force, when V is equal to 0, is equal to AB. So as long as there's some sort of net force on the trolley when it's at rest, there should be some eventual movement. So no, just because the power is 0 at time 0 doesn't mean that the trolley can't start from rest. And there we go. That's question 10, which was a pretty decent power question. I'm actually quite surprised that they were able to give us a good power question here, because that's rare. I mean, as far as the AP exam is concerned, they probably won't ask about power that much, if at all. Power is kind of the ugly duckling of mechanics. It becomes more important in electricity and magnetism, but for mechanics, there's not that much they can ask you about as far as power is concerned. So the next one says the force exerted on an object is F equals F0 times x over x0 minus 1 times I hat. Find the work done in moving the object from x equals 0 to x equals 3x0 by plotting the function and finding the area under the curve, and by evaluating the integral analytically. Okay, so I guess the graph is going to be, it looks like a simple linear graph, so you could just calculate area under the curve without knowing any calculus, but the function given is f equals f0 times the ratio of variable x over some constant x0 minus 1 times I hat. So it's just in the positive x direction. And it says find the work done in moving from x equals 0 to x equals 3x0, first by using a graph, then by using just integration. Work from x0 to 3x0. Okay, so let's see how this would work out. When x equals 0, it's just going to be force equals F0 times, well, nothing minus 1. So the force actually starts out at negative. So here's force versus position. The force actually starts out at some negative value F0 over here. And eventually, once x reaches x0, you get 1 minus 1. So this will be at x0. And it should be linear, right? Constant, constant, and minus a constant. Yeah, it should just be a linear graph. And this is why you can do it without calculus. So there's x0, there's 2x0, and roughly there would be 3x0. Okay, and if we want to figure out the work done by the force, shouldn't be too hard to do if we just calculate the area of that triangle. Let's see, so at 3x0, that would be 3x0 over x0 is 3, 3 minus 1 is 2, so f0 times 2. So this over here is 2f0. And then at x0 itself, we know that's 0. So yeah, the width of this from x0 to 3x0, that width, be very careful, is 2x0. Subtract these from each other. And area of the triangle then, work equals area equals 1/2 base times height. I guess one of those 2's cancels and you're left with 2 f0 x0. Okay, that was through graphical methods. Now they said do it analytically, so using just math. So we will do integral of f dx. So work equals integral of f of x dx. And that's going to be from, this is a definite integral. We have a starting point and an ending point. That's from x0 to 3x0. So that's going to equal integral from x0 to 3x0 of let's see, I can pull the f0 factor out of the integral, just make things look a little bit nicer, and then I'm going to write it as 1 over x0 times x minus 1 and integrate with respect to x. Okay, integral of x is going to be x squared and then divide by 2. Integral of -1 is just going to be negative x. So we have f0 times 1 over x0 times x squared over 2 minus x. And then we're evaluating that from x0 to 3x0. So that's going to equal f0 times 1 over x0 times 3x0 squared over 2 minus 3x0 minus, so I'll put, yeah, let's make some brackets there, and then minus another set of parentheses. Now we plug in x0, the bottom bound, so that's going to be 1 over x0, and then x0 squared over 2 minus, plug in x0 for x, and close the bigger brackets. Let's see, so that's going to be 9x0 squared over 2, and then over here it's going to be minus 1x0 squared over 2, so 9 minus 1, that's 8x0 squared over 2, which reduces to 4x0 squared, and then they're both divided by this x0. So that's 4x0. So that's 4x0. And then we've got negative 3x0 minus negative 1x0. So that's negative 2x0. So I've got 4x0 minus 2x0 is 2x0. And then all that times the f0 out in front. Yep, we get 2 f0 x0. Same result as we got using graphical methods. All right. What else do I have on my list here? Oh God, we've gone over 5 hours. So we did that one and that one. What does this one say? Okay, this next one says we have a stiff spring has a force law given by F equals negative kx cubed. So it's not your typical spring. This one has a force that increases with x cubed rather than increasing with x. The work required to stretch the spring from the relaxed state x equals 0 to the stretched length x equals L is W0. In terms of W0, how much work is required to extend the spring from the stretched length L to the length 2L? Okay, I think that should be a pretty easy one to set up. I think that little bit of space that we have down there might just be enough for it, actually. So they want us to figure out how much work is required to extend the spring from the stretched length L to the length 2L. Okay, so work required. So the force that the spring exerts is negative kx cubed, which means the external force required to stretch it is positive kx cubed. So work is the integral of f dx. The displacement of the spring, the stretching, would be in the direction that that external force is pulling. So the cosine theta part of the work equation is just going to be cosine of 0, which is equal to 1. So we just do integral of kx cubed dx. And that will be x cubed becomes x to the 4th, and divide by that new 4. So we get 1/4 kx to the 4th. We get 1/4 kx to the 4th. And then from there, they said W0 is the work necessary to stretch it by a distance L. So W0 is going to be 1/4 kL to the 4th, the way they've defined it. And they want how much work is required to extend the spring from the stretched length L to the length 2L. So work of 2L is going to be 1/4 k times 2L to the 4th power. If I take 2L to the 4th power, 2 to the 4th is 16. And then L to the 4th. So I get 16 times 1/4 kL to the 4th. And they said how much work is done stretching it from L to 2L, not from 0 to 2L. This is from 0 to 2L. From L to 2L, it would be just subtract 16 of 1/4 kL to the 4th minus minus 1 of 1/4 kl to the fourth, that would be 15 of 1/4 kl to the fourth, or 15 times W0. So work done, work from L to 2L would be 15 times W0. All done. Now the next set is on another page. We've got 6 more on my list, assuming I don't decide to skip any. Let's see, so there's a multiple choice one, which says what? Multiple choice number 10, what do you have? It says a particle with total energy E moves in one dimension in a region where the potential energy is U of X. A particle with total energy E moves in one dimension in a region where potential energy is U of X. So, total energy, that's the total mechanical energy. They just called that E. Potential energy, they called it U of X. And they've got 2 questions. The first question, and it looks like the answer choices are the same for both questions. So the first question is, what is the speed of the speed of the particle is 0, where which of the following? So the answer choices are U of X equals E, U of X equals 0, du of X dx is 0, and d squared U of X dx squared is 0. Those are the 4 answer choices. So the first question is, under which of those 4 conditions is the speed of the particle 0? Under which of those 4 conditions a particle with total energy E moves in one dimension in a region where the potential energy is U of X? So under which of those is it 0? Is the speed 0? That would be where the kinetic energy is 0, and the kinetic energy is 0 when all of the mechanical energy is in the form of potential energy. That would have to be choice A. Now the second question says the acceleration of the particle is 0 where, again, which of these 4? Under which of these 4 conditions is the acceleration equal to 0? Well, the acceleration would be 0 where the net force is 0, and assuming the only force at play here is whatever conservative force this potential energy is associated with, we're looking for where the force is 0. And as you might remember from earlier, we can get force from potential energy by doing what? By taking the negative derivative of potential energy. I mean, in this case, if we want the force to be 0, it doesn't matter whether it's the positive or the negative. So, yeah, for the first question, choice A was correct. For the second question, force is 0, where du dx is 0. And that is the end of that multiple choice question. Next we have, it looks like 2 exercises and 3 problems. What do we have? The exercise here says in one dimension, the magnitude of the gravitational force of attraction between a particle of mass m1 and another particle of mass m2 is given by, and then they did Newton's law of universal gravitation. What is the potential energy function? How much work is required to increase the separation of the particles from x equals x1 to x equals x1 plus d? We already kind of did this earlier. Yeah, I think the reason I listed this was to remind myself to actually do the derivation of the potential energy formula under the universal version of the force of gravity. Okay, we'll skip that one. Here we have number 3 says, a particle moves along the x-axis under the influence of a conservative force that is described by, have a look at this, f of x equals negative alpha x e to the negative beta x squared I hat. So it's in the, well, we've got a negative here, so it must be in the negative x direction. And it says where alpha and beta are constants, which is what I would have assumed, find the potential energy function u of x. Oh, wait, actually, can we do this? Yeah, we can. For a minute there, I thought it was going to require, like, some calculus techniques that you didn't learn from me, so false alarm. We can do this one. This is doable. So yeah, find the potential energy function u of x. Find u of x. All right, well, we know from earlier u of x is just going to be negative integral of f of x dx. And I guess we need to take direction into consideration, don't we? Let's see. So the direction of the force is in the negative direction. The direction of the, well, yeah, that's already taken into account by this negative sign over here. Okay, yeah, we're good. We don't need to worry about the cosine theta. Or do we? No, we don't, because the negative sign is already, yeah, it's accounted for. So if we go ahead and take the negative integral of negative alpha x e to the negative beta x squared dx. These negatives cancel out. I can pull the alpha constant out. I can factor it out of the integral. And then inside the integral, I've got x e to the negative beta x squared. Okay, this calls for a u substitution. So I'm going to do u equals negative beta x squared. And that gives me du dx equals the derivative of negative beta x squared is negative 2 beta x. And move the x over to the right hand side and we get du equals negative 2 beta x dx. Okay, so I can take out a negative 2 beta x dx and replace it with a du. Well, I've got an x and I've got a dx. I need a negative 2 beta, so we will multiply by negative 2 beta over negative 2 beta. So times negative 2 beta, and also divide by negative 2 beta in order to make sure that we aren't changing the overall value of this integral. Okay, so now we've got negative 2 beta x dx. We can take this and replace it with du. So we have negative alpha over 2 beta, integral of that stuff is gone and replaced with du, and then e to the negative beta x squared just becomes e to the u. The integral of e to the u is e to the u. So we have negative alpha over 2 beta times e to the u plus c, and then if we replace the u, if we sub back in negative beta x squared, then we have negative alpha over 2 beta e to the negative beta x squared plus c for our potential energy function. Do we have enough information to write something down for the value of c? It doesn't look like it. So yeah, that's as far as we go with that one. I am a little bit worried that maybe, just maybe, I missed a negative somewhere, but if I did, I will look back on it and probably post something in a pinned comment with a correction. Now then, what else do I have on my list? 3 more over here. Let's see if they're any good. This one, force on a particle constraint to move along the z-axis is given by that messy looking function. Assume that, okay, find an exact expression for... Okay, so it's just another force where they want us to find a potential energy function. So just another take the negative integral. Yeah, I don't know. It looks like it's going to be hideous. I'll write it down, but I don't know about actually doing it. I'll just write it down for you guys to try out on your own. So it says we've got a force in the z direction, and is dependent on z, equals k over z plus L squared minus k over z minus L squared. And they want you to find a potential energy function for it. They say u of z approaches 0 as z approaches infinity. So use that as your initial value, essentially. Once you do your integral, set it so that, I guess you would be integrating between 2 points. So you would be integrating between some specific point z0, and then some final point z infinity, and then whatever you get for z infinity, just set that potential energy equal to 0 and get your potential energy function for just one position. Z0 is essentially what they're saying. Kind of the same thing that we did for gravitation, really. I mean, what did we do with, with gravitation over here, we got potential energy 2 minus potential energy 1. If you think of it as potential energy 1, setting it to R infinity, then you just get potential energy at some position R is equal to negative gmm over R. That's essentially what they're asking you to do here. But yeah, integrating this, so you would probably want to do a U substitution here, unless you can kind of see in your head that the U substitution isn't going to give you any like constants over here. If you have enough practice with U substitution that you don't need to do that, then fine, but if all else fails, you would integrate these. I would advise you, if you don't have that much experience with calculus, to integrate these separately. So integrate this part separately from this part, and z plus L squared and z minus L squared, I would rewrite them as z plus L to the negative 2 and z minus L to the negative 2. I would factor the k out of the whole entire expression just to get it out of the way, and then just use power rule. It's going to be very, very similar to what we get over here. Only difference is, instead of r's in the denominators, you're going to have z plus L and z minus L as your denominators. That would be the major difference, but otherwise it should look similar to that. So if you're getting something that looks way too far off from what we get for gravitational potential energy, then you've probably made a mistake somewhere. But I will leave that one alone for you guys to try out. And let's see, we also had this one. Says a chain is held on a frictionless table with 1/4 of its length hanging over the edge, as shown in the figure, which I will draw for you. If the chain has a length L and a mass m, so they've got a table here, and then they've got a chain hanging over the edge of the table. And they're saying, if the chain has a length L and a mass m, length capital L and mass lowercase m, how much work is required to pull the hanging part back on the table? How much work is required to pull the hanging part back on the table? They said 1/4 of its length is hanging over the edge. So this right here is 1/4 of the full length, and therefore it's 1/4 of the full mass, and I guess I need to draw this even longer. And this is supposed to be 3/4 of the length. This is supposed to be 3/4 of the length. And there's gonna be some force applied over here to pull this thing up. They said the table is frictionless, so normal force and gravitational force over here are gonna cancel each other out. So for the part of the chain that's on the table, only the force applied really exists. But for the, well, the force applied and the force of tension. The force applied, and there's going to be some sort of tension force. So it says how much work is required to pull the hanging part back on the table. Well, for the hanging part, what we would want to do is we would need to, I guess, chop this thing into little pieces. And then each piece is going to be a tiny bit of the total mass. And each one is going to need to be lifted a different height. So this part over here on top is not going to require that much work to pull back up, but for example, the bottom link of the chain, the last part of the chain, it needs to be lifted the highest, it needs to be lifted the most, so more work is going to be done on that part than, say, this top part of the hanging section. Let's see. Is it really just as simple as doing... Actually, we might not even need calculus at all here. Yeah, I don't think we need calculus here, because we could just do the change in potential energy of the center of mass of the hanging part. We just need the change in potential energy of the center of mass of this hanging part to actually, I can't tell if I'm overthinking it or oversimplifying it at this point. Maybe streaming for 5 hours straight isn't good for the brain. Let's see, because we could just... So there's going to be a force of gravity acting on each link of the chain. So on each little bit of the chain, there's going to be a force of gravity acting downward, and there's going to be some force of tension pulling it up. And that force of tension need not be any more than the weight of the chain that is still hanging. So yeah, the force of tension would start out high and then would decrease as more and more of the chain ended up resting on the table. So work would just be the integral of that tension force times, I guess we'll call it times dl. Where L is going to be the length of chain being pulled from, let's see, do I want to define L equals 0 to be down here or over here? I think I want L equals 0 to be defined down here, and then go up to up here, I would define that as L equals 1/4 of big L. And then if I define things that way, then force of tension has to equal exactly the weight of the remaining chain. So force of tension as a function of L would be, well, it would start off as it would start off as 1/4 of the mass of the chain times G, and then it would be minus total mass over total length times the length of chain already pulled. Right? The mass per length times the length. So when it's been pulled half the way up, or rather 1/8 of the total length of the chain up, that would be 1/8, 1/4 minus 1. Yep, that works, yeah. And then times G. Okay, yeah, I think this will work. I think this should work nicely for us. So the force of tension is going to be just this 1/4 mg minus m over L times m over big L times little l, the length of chain that has been pulled so far. Okay, that should do it. So then we get integral from L equals 0 to L equals 1/4 of big L of this whole expression, F of L, force tension of L dl. And let's see what we can do with that. So that would be I'll factor out the g, factor it out of the integral, and then we've got 1/4 m minus m over big L times L dl. Okay, 1/4 m integrated with respect to L is just going to be 1/4 ml minus m over big L is a constant, so it stays out, and then times the integral of L, that becomes L to the second power divided by 2, so L squared over 2. And we're evaluating that from 0 to 1/4 of big L. So that's going to be G times 1/4 m times 1/4 big L, plugging in the top bound, minus m over L times 1/4 big L squared over 2, and then close those parentheses, minus 1/4 m, whoops, 1/4, not 1/mth, 1/4 m times L equals 0 minus m over big L times 0 squared over 2. Okay, so this whole thing is fortunately 0. That saves us a ton of work that we otherwise would have had to do. And we get, let's see what we can do here. So this is a fourth times a fourth is a 16th ml, 1/16 ml, and then minus, this is going to be 1/16 L squared over 2, so that's half of 1/16 ml squared over L. That's half of 1/16 ml, since the L squared and the L reduce. So we're left with, G times, is that still visible on the screen? Yes, it is. G times, this is going to be 1/16 ml minus L squared and L reduce. So we've got ml, and then we've got the 1/4 squared is 1/16 over 2. So 1/2 of 1/16 ml. Okay, 1/16 ml minus half of 1/16 ml is half of 1/16 ml. So that'll be 1/2 of 1/16 or 1/32 of ml times G. I believe I did this correctly, but if I made a mistake somewhere, I will comment on it in a pinned comment whenever I get around to reviewing and timestamping this video in a few days. But I believe this to be correct. Whatever force we apply here should be just enough to cause the necessary amount of tension needed to lift this thing. So 1/32 of mgl. Let me see if we can glean any sort of meaning from this. So 1/32. Well, if we have 1/4 of the length, and therefore 1/4 of the mass, so let me think about this. So compare it to if we treated it as a constant force and we were just displacing it by a displacement of 1/4 L, that would definitely be an overestimate of the total work. We actually do less work than that because the amount of mass that needs to be pulled and the weight that we have to fight against is decreasing. So an overestimate of this would be a displacement of 1/4 L. So overestimate would be if we assumed that the force required is 1/4 mg, the full weight of the whole chain, and that the displacement, I guess delta y in this case, would be 1/4 L. If we multiplied these, then the overestimated work would be 1/4 mg times 1/4 L equals 1/16 mgl, and in fact the actual work is half of that overestimate. Yeah, that does make sense to me. Because essentially what you're doing is you're moving the center of mass by half of that distance. Yeah, that makes sense to me. I think we got it right. And if any corrections are needed, come back in a few days and there'll probably be a pinned comment talking about it. Or I'll mention it in the next stream if I end up reviewing this early enough. It looks like we have one or two more. Which one was this? Okay, I think there's one more here before we have to call it a day. So this one says a 1.18 kilogram object is acted on by a net conservative force given exactly by F sub x equals negative 3x minus 5x squared. Find the potential energy of the system at x equals 2.26 meters. Assume that u of 0 is equal to 0. So they've given us an initial condition, which will allow us to solve for the constant of integration. And then part B says the object has a speed of 4.13 meters per second in the negative x direction when it is at x equals 4.91 meters. Find its speed as it passes x equals 1.77 meters. That should just be regular conservation of energy, I imagine. Okay, let's go ahead and start a new sheet for this. And this should be our last problem of the day. Oh my goodness. I was joking when I said we were going to be doing like 6 hours or whatever it was I said in the beginning. But we actually did it. It's a good thing I had the whole day off today. Okay, so right down we had f sub x as a function of x is equal to negative 3x minus 5x squared. And they told us this was a conservative force, and the mass is 1.18 kilograms. Find the potential energy of the system at x equals 2.26 meters. Find u of 2.26. And they're saying assume u of 0 is equal to 0. Okay, so all we have to do is take the negative integral of this. So delta u is equal to negative integral of f of x dx equals, or, well, delta u, or in this case, since we have an initial condition, we can just say u of x. Yeah, we don't need the delta here. So u of x equals negative integral of f of x dx. That's negative integral of negative 3x minus 5x squared dx. If I distribute the negatives, then I just get 3x plus 5x squared and then if I integrate that, I would get integral of x is x squared over 2, so that's 3 over 2 x squared. And then we've got integral of x squared is x cubed over 3, so that's plus 5 thirds x cubed, and then plus a constant, and then we have u of 0 equals 0, so 3/2 of 0 squared plus 5/3 of 0 cubed plus c, that's a 0, that's a 0, so that means that c equals 0. Okay, so our u of x complete form is 3/2 x squared plus 5/3 x cubed. And they want u of 2.26. Just plug 2.26 in there and you're good to go. Then for part B, it says the object has a speed of 4.13 meters per second in the negative x direction when it is at x equals 4.91 meters. Find its speed as it passes x equals 1.77 meters. The fact that it's in the negative direction shouldn't matter because kinetic energy uses the square of the magnitude of the speed. The square of the speed, which is another way of saying the square of the magnitude of the velocity. So yeah, it shouldn't matter that they mention it's in the negative direction. The only reason that matters is because they say find its speed as it passes x equals 1.77 meters when it used to be at 4.91. So at the very least, telling us that it's negative helps us understand that this thing was moving to the left instead of the natural assumption that the object would be moving in a positive direction unless otherwise specified. So at least they indirectly justified that. But yeah, so what I would do is say kinetic energy at 4.91 meters, kinetic energy at 4.91 meters is equal to 1/2 m, so 1/2 of 1.18 times v squared. They said v was 4.13 meters per second, so that squared. So that's kinetic energy at time 4.91, or at position 4.91 rather. And then potential energy at 4.91, you can just calculate it from the formula we got before, 3/2 of 4.91 squared plus 5/3 of 4.91 cubed. That's all stuff that you can plug into a calculator on your own. You don't need me to do that for you. Add these up, and that will give you your total mechanical energy. And then from there, use conservation of mechanical energy to figure out what is the kinetic energy when you are at 1.77 meters is going to equal mechanical energy total minus whatever the potential energy is at 1.77. And then once you have your kinetic energy, multiply by 2, divide by m, and take the square root, and you will have the speed. That's going to equal 1/2 1.18 times v squared. Solve for v. You have everything you need to do the rest. The calculus part is already done. And yeah, I guess that will be the end for today. How much do I even have left? So we've got, let me go through the list real quick. So we did all the kinematics stuff. We did force stuff. Yep, cross all that out. I did all this and did all that. And that leaves us with a couple of quick things in momentum. Rotational kinematics is probably going to be like a flyby because the calculus of rotational kinematics is the same as the calculus of regular kinematics. It's really not going to be all that surprising. There are a couple of things that I want to show in torque, some of which are not going to be on your AP exam, but I feel like they're worth showing anyway. Some stuff that might involve practicing a little bit more with the unit vector notation. So momentum, rotational kinematics, torque, some angular momentum stuff, not that many things for angular momentum really. So really torque and angular momentum are basically going to be part of a single thing. For center of mass and moment of inertia, we do need to, let me see on this other sheet of notes. We already did that and that and that. We did that. We did this. We did this. We did this. We did this. We already did this ahead of time. Oh, okay, we've got those two things we need to cover for gravitation. And then, yeah, for rotational dynamics, we do need to look at the calculus version of the center of mass formula. I already gave you the algebra version a while ago. For moment of inertia, I already have some examples in my Riemann sums videos, which I directed you to in the previous stream. And once I get around to time stamping and doing all that, I'll put it in the iCard button that shows up in the corner of the video sometimes, so that you can also just click on it through there. And I think now it also shows those in the description of the video, so whenever I get around to time stamping this, that will show up. But you should be able to look up the videos just fine. You don't have to wait for me. Just look up the videos that I have titled something to do with Riemann sums. There's 2 of them, at least at the time of this recording. There might be more in the future depending on when you watch this. But yeah, some moment of inertia calculations, if you want to preview that, it's in there. I might do one next time, but no more than that since I've already done the work in previous videos. That formula needs to be covered, and that one, and that's a pretty simple one. Oh, right, and proving that. And then for simple harmonic motion, there isn't really anything of note, just one equation that you have to know. And yeah, I think we'll be able to get through the second half a little bit quicker than today, but we'll see. I mean, if it takes 6 hours for that second half, then it's not even exactly a half, I don't think. But yeah, if it takes 6 hours for that, then at least the silver lining will be that I never ever have to do it again, because the video will be there forever. Oh, hello. Well, I just finished. We're done for today, but I'm teaching for AP Physics C Mechanics. So if you're taking or planning on taking an AP Physics course this year, I've been busy doing AP Physics 1 and AP Physics C Mechanics, and if you're interested in the other AP Physics courses, maybe I will start covering those in the next year. I'm not entirely sure. But yeah, we are very nearly done. We've got one more of these videos for Physics C, and that will be next time. And then after that, for both Physics 1 and Physics C, we are going to have just a little bit of final advice and reminders and a couple of extra topics relating to the test that fell through the cracks. and maybe I will look at a few example questions from past AP tests here and there, a couple of relevant examples to illustrate some of the advice that I will be giving and some of the reminders, and then that will be the end. And I'm going to give myself a little bit of a break to work on some other projects that I've been putting on hold. I'm from a different country, also studying physics, but electricity current right now. Yeah, I'm mostly teaching for an American audience, and I imagine there are probably some Europeans and Canadians watching because the AP program is available in other countries too. But yeah, this is for a college physics course that students can take early in high school. So that's what AP Physics is. The AP stands for Advanced Placement. If you take the exam and score well on it, then you get credit. You get some college credit, and maybe you can skip some courses when you start off college. Might be able to graduate a little bit early. And you get to save a lot of money since you won't be paying tuition for those courses that you skip. But of course, some colleges do not accept your AP credit, so it might not be worth it to do well on the exam. I mean, I'd say it's worth it anyway, as long as learning is the goal. As long as you learn something, it's always worth it. But yeah, you can find out more about the AP program if you just look up the AP courses from College Board. That's the name of the organization that administers the AP exam. It's called just the College Board. I'm not too fond of all the decisions that they make. I might actually be posting a rant about a certain something that they have written on one of the pages for the old free response questions, but we'll worry about that once the course is actually done. So yeah, if you have never imagined me ranting before, you might not have to imagine it in a couple days or weeks once I have the free time to actually record my mini rant. Can you tell me the resistance in an infinite tube of radius r, and inside there is one more tube of radius r, so current is flowing perpendicular to the inner tube, then can you find the resistance? So electricity and magnetism. Resistance in an infinite tube of radius r, and inside there's another tube of radius little r, so current is flowing perpendicular to the inner tube. Then can you find the resistance? Well, that does seem like a familiar enough problem. I don't know if I have enough information, though, to determine the resistance here. So you've got an infinite cylindrical tube of radius big R, and then within it is another tube, so the picture I'm imagining looks like this. And then the length of the tube, of course, is infinite, and then this radius is going to be little r. And then this radius over here is going to be little r. And can you find the resistance? Well, I don't really know anything else about this tube, like what material is it made of, how much current is running through it, what kind of voltage do we have across it, what is the resistivity of the material. I don't think we have enough information to answer that. mean, I have seen problems that look like this, but I don't know what you want me to do when all I know is the inner and outer radius. Only variable, not in numbers. Well, I understand that, but the only two variables I have are these two radii. That's not enough to determine a resistance. Like, even if you gave me like the resistivity as a variable, I suppose then we could say that the resistivity of the inner material would be like rho inner, and then resistivity of the outer material would be rho outer. And then we could say resistance is equal to, let's see, it would be resistivity times length over area and I suppose we could compare the cross-sectional areas. Yeah, I don't really know. If we have an infinite length here, I would need more time to think about this. I would need more time to think about like what kinds of assumptions need to be made here, and also just give myself a refresher on how to deal with an infinite length resistor. Unfortunately, the topic for today was planned to be mechanics, so that is where I'm gonna have to wrap things up for today. I'll probably reopen my open-ended office hours for questions like this in the next school year. But for today, that will be the end. So for those of you in AP Physics Mechanics, sorry for that little detour. Hopefully you gained something of value today. Hopefully this helps you feel a little bit more confident about that upcoming exam. Take care, keep studying, try out some of those questions that I didn't solve for you. See if you can finish the parts that I suggested you do on your own. And I will see you in the next one. Until then, class dismissed. Have a good one.